Chapter 13 Ethereum Development Environment. This chapter introduces the Ethereum development environment. Several examples will be presented in this chapter to complement the theoretical concepts provided in the earlier chapters. This chapter will mainly cover the setup of the development environment and how to use relevant tools to create and deploy smart contracts using the Ethereum blockchain. The first task is to set up an Ethereum development environment. This involves setting up a private net and installing tools that aid the development of a decentralization application on Ethereum. We will also look at testnets, which can play a vital role in testing the smart contracts before deploying on the mainnet. Ethereum has several testnets. A common testnet is called Ropsten, and is used by developers or users as a test platform to test smart contracts and other blockchain-related proposals. Then we will look at the private net option in Ethereum, which allows the creation of an independent private network. This private network can be used as a shared distributed ledger between participating entities and for the development and testing of smart contracts. While there are other clients available for Ethereum, Geth is the leading client for Ethereum and the standard tool of choice, and as such, this chapter uses Geth for the examples. There are various ways to perform development for Ethereum blockchain. We will see some of the most popular options in this chapter. The topics that we will cover in this chapter are listed here. Test networks, private network components, starting up the private network, mining on the private network, Remix IDE, MetaMask, using MetaMask and Remix IDE to deploy a smart contract. Overview. There are multiple ways to develop smart contracts on Ethereum. A usable and sensible approach is to develop and test Ethereum smart contracts either in a local private net or a simulated environment like Ganache. Then it can be deployed on a public testnet. After all the relevant tests are successful on a public testnet, the contracts can then be deployed to the public mainnet. There are, however, variations in this process. Many developers opt to only develop and test contracts on a local simulated environment and then deploy onto the public mainnet or their private enterprise production blockchain networks. Developing first on a simulated environment and then deploying directly to a public network can lead to faster time to production, as setting up private networks may take longer compared to setting a local development environment with a blockchain simulator. We will explore all these approaches in Chapter 14, Development Tools and Frameworks, and Chapter 15, Introducing Web3. There are new tools and frameworks available like Truffle and Ganache, which make development and testing for Ethereum easier. We will look into these tools in more depth in Chapter 14, Development Tools and Frameworks. But first, we will use a manual approach whereby we develop a smart contract and deploy it manually via the command line to the private network. This will allow us to see what actually happens in the background. Also, we will cover the use of MetaMask as it has become the tool of choice for developers. Frameworks and tools make development easier, but hide most of the finer under-the-hood details that are useful for beginners to understand to build a strong foundation of knowledge. Therefore, first, we will demonstrate development using the native tools available in Ethereum, and once we have understood all the foundational knowledge, we can start using development frameworks like Truffle, which indeed makes development and testing very easy. Let us start by connecting to a test network. Test networks. The Ethereum Go client, geth.ethereum.org. Geth can be connected to the test network using the following command, $geth-testnet. This command will connect to the Ropsten network, which is a pre-configured proof-of-work POW test network. A sample output is shown in the following screenshot. The screenshot shows the type of the network chosen and various other pieces of information regarding the blockchain download. A blockchain explorer for testnet is located at ropsten.etherscan.io and can be used to trace transactions and blocks on the Ethereum test network. There are other test networks available too, such as Rinkeby and Goerli, also referred to as Goerli. Geth can be issued with a command line flag to connect to the desired network. Now let us experiment with building a private network, and then we will see how a contract can be deployed on this network using MIST and command line tools. Components of a private network. A private net allows the creation of an entirely new blockchain, usually on a local network. This is different from testnet or mainnet in the sense that it uses its own Genesis block and network ID. In order to create a private net, 3 components are needed: network ID, the Genesis file, data directory to store blockchain data. Even though the data directory does not strictly need to be mentioned, if there is more than one blockchain already active on the system, then the data directory should be specified so that a separate directory is used for the new blockchain. On the mainnet, the Geth Ethereum client is capable of discovering boot nodes by default as they are hard-coded in the Geth client, and connects automatically but on a private network. Geth needs to be configured by specifying appropriate flags and configurations in order for it to discover or be discoverable by other peers. We will see how this is achieved shortly. In addition to the previously mentioned 3 components, it is desirable that you disable node discovery so that other nodes on the internet cannot discover your private network, and so that it is secure. This can be achieved by running Geth with the flag --node discover, which disables the peer discovery mechanism. If other networks happen to have the same Genesis file and network ID, they may connect to your private net, which can result in security issues. The chance of having the same network ID and Genesis block is very low, but nevertheless disabling node discovery is a good practice and is recommended. Another network or node connecting to your private network can result in security breaches, information leakage, and other undesirable security incidents. However, note that private keys are usually run with the enterprise environments and are protected by usual enterprise security practices such as firewalls. Disabling peer discovery also allows us to define a list of static peers that we have on our network. This gives us the additional ability to control who can join our private network. Just before we move on to creating our private network, let's get some theoretical aspects covered that are related to discovery and understand what actually happens when we disable node discovery. For this, first we'll see how a node normally discovers other nodes on an Ethereum network and what protocols are involved to do so. The suite or protocols that is responsible for node discovery and communication between Ethereum nodes is called RLPX. Ethereum node discovery is based on the Kademlia protocol. Kademlia is a UDP-based distribution hash table (DHT) protocol for distributed peer-to-peer networks. The Ethereum network consists of 4 elements or layers: discovery, RLPX, dev P2P, and application-level subprotocols. The discovery protocol is responsible for discovering other nodes on the network by using node discovery mechanism based on Kademlia protocol's routing algorithm. This protocol works by using UDP. In Ethereum, there are 2 discovery protocols, named DiskV4 and DiskV5. DiskV4 is currently production-ready and implemented in Ethereum, whereas DiskV5 is in development. For discovery, a new Ethereum node joining the network makes use of hard-coded bootstrap nodes, which provide an initial entry point into the network, from which further discovery processes then start. This list of bootstrap nodes can be found here in the bootnodes.go file. RLPX is a TCP-based transport protocol responsible for enabling secure communication between Ethereum nodes. It achieves this by using an asymmetric encryption mechanism called Elliptic Curve Integration Encryption Scheme, ECIES, for handshaking and key exchange. Dev P2P, also called the Wire Protocol, is responsible for negotiating an application session between 2 nodes that have been discovered and have established a secure channel using RLPX. This is where the hello message is sent between nodes, to provide each other with details of the version of the dev P2P protocol, the client name, supported application subprotocols, and the port numbers the nodes are listening on. Ping and pong messages are used to check the availability of the nodes, and disconnect is sent if a response from a node is not received. Finally, the fourth element of the Ethereum network stack is where different Ethereum subprotocols exist. After discovering and establishing a secure transport channel and negotiating an application session, the nodes exchange messages using so-called capability protocols, or application subprotocols. This includes ETH, versions 62, 63, and 64, Light Ethereum Subprotocol LES, Whisper, and Swarm. These capability protocols are responsible for different application-level communications. For example, ETH is responsible for block synchronization. It makes use of several protocol messages such as status, transactions, get block headers, and get block bodies messages to exchange blockchain information between nodes. Note that ETH is also referred to as Ethereum Wire Protocol. All four of these elements can be visualized in the following diagram. So here in our example, when we use the --node discover flag, it disables the peer discovery mechanism described previously. We can then add nodes manually to the network by maintaining a static list of peers. Now, after this introduction to understand some underlying theory, all the parameters required for creating a private network will be discussed in detail. Network ID. The network ID can be any positive number except any number that is already in use by another Ethereum network. For example, 1 and 3 are in use by Ethereum mainnet and testnet, Ropsten, respectively. Network ID 786 has been chosen for the example private network discussed later in this section. The Genesis file. The Genesis file contains the necessary fields required for a custom Genesis block. This is the first block in the network and does not point to any previous block. The Ethereum protocol performs checking in order to ensure that no other node on the network can participate in the consensus mechanism unless they have the same Genesis block. Chain ID is usually used as an identification of the network. A custom Genesis file that will be used later in the example is shown here. This file is saved as a text file with the JSON extension, for example, privategenesis.json. Optionally, Ether can be pre-allocated by specifying the beneficiary's addresses and the amount of Wei, but this is usually not necessary as being on the private network, Ether can be mined very quickly. In order to pre-allocate an account with Ether, a section can be added to the Genesis file, as shown here. Now let's see what each of these parameters means. Nonce. This is a 64-bit hash used to prove that POW has been sufficiently completed. This works in combination with the mixhash parameter. Timestamp. This is the Unix timestamp of the block. This is used to verify the sequence of the blocks and for difficulty adjustment. For example, if blocks are being generated too quickly, that difficulty goes higher. Parent hash. Being the Genesis first block, this is always 0 as there is no parent block. Extra data. This parameter allows a 32-bit arbitrary value to be saved with the block. Gas limit. This is the limit on the expenditure of gas per block. Difficulty. This parameter is used to determine the mining target. It represents the difficulty level of the hash required to prove the POW. Mix hash. This is a 256-bit hash that works in combination with nonce to prove that a sufficient amount of computational resources has been spent in order to complete the POW requirements. Coinbase. This is the 160-bit address where the mining reward is sent as a result of successful mining. Alloc. This parameter contains the list of pre-allocated wallets. The long hex digit is the account to which the balance is allocated. Config. This section contains various configuration information defining the chain ID and blockchain hard fork block numbers. This parameter is not required to be used in private networks. Data directory. This is the directory where the blockchain data for the private Ethereum network will be saved. For example, in the following example, it is ~ether_private/. In the Geth client, a number of parameters are specified in order to run the Ethereum node, fine-tune the configuration, and launch the private network. These flags are listed in the following section. If connectivity to only specific nodes is required, which is usually the case in private networks, then a list of static nodes is provided as a JSON file. This configuration file is read by the Geth client at the time of starting up, and the Geth client only connects to the peers that are present in the configuration file. Flags and their meaning. The following are the flags used with the Geth client. --no discover. This flag disables the peer discovery mechanism, which allows you to add specific peers manually. --max peers. This flag is used to specify the number of peers allowed to be connected to the private net. If it is set to 0, then no one will be able to connect, which might be desirable in a few scenarios such as private testing. --RPC. This is used to enable the RPC interface in Geth. --RPCAPI. This flag takes a list of APIs to be allowed as a parameter. For example, ETH Web3 will enable the ETH and Web3 interface over RPC. --RPC port. This sets up the TCP RPC port, for example 9999. --RPC ORS domain. This flag specifies the URL that is allowed to connect to the private Geth node and perform RPC operations. --port. This specifies the TCP port that will be used to listen to the incoming connections from other peers. --identity. This flag is a string that specifies the name of a private node. Static nodes. In the case of private networks, usually the connectivity is limited to a specific set of peers. In order to configure this list, the node ID of these nodes are added to a configuration file called staticnodes.json. This file is usually placed in the data directory of the Geth Ethereum client executable. This directory is also where the chain data, database, and key store files are saved. By default, the data directory is located at user's home directory, library Ethereum, but can be configured by using the flag --data dir. The file name could be staticnodes.json under the data directory. This is valuable in a private network because this way the network is limited to only known nodes. An example of the staticnodes.json file is shown as follows. Here, XXX is the IP address and TC port can be any valid and available TC port on the system. The long hex string is the node ID. As we now understand the various aspects and components required to set up a private network, including the Genesis file and other relevant configuration files, let's now move on to actually setting up our own private network using Ethereum. Starting up the private network. First, let's start up our private network and prepare it for use. The first step is to create a directory named etherprivate under the home directory of the user. $mkdir ~etherprivate. This command will create the directory. Once the directory is created, place the private Genesis.json file shown earlier in the Genesis file section. At this point, stored under the home directory of the user, we have a directory named etherprivate, which contains the Genesis file called privategenesis.json. We are ready to start our network. The initial command to start the private network is shown as follows. This output indicates that a Genesis block has been created successfully. In order for Geth to start, the following command can be issued. This will produce the following output. An important part of the output to note is the following log lines. These lines show the information about the Inter-Process Communications IPC endpoint, HTTP endpoint, and Ether-based Coinbase account information. This information is useful for the examples provided later in this section. Now Geth can be attached via IPC to the running Geth client on a private network using the following command. As shown in figure 13.5, this will open the interactive JavaScript console for the running private net session. Note that the time of the last block creation is also shown, seen in the preceding output. You may notice that a warning message appears when Geth starts up. This message appears because there are no accounts currently available in the new test network and no account is set as Ether-based to receive mining rewards. This issue can be addressed by creating a new account and setting that account as Ether-based. This will also be required when mining is carried out on the test network. This is shown in the following commands. Note that these commands are entered in the Geth JavaScript console, which is shown in the preceding screenshot. The following command creates a new account. In this context, the account will be created on the private network ID 786. Once the account is created, the next step is to set it as an Ether-based Coinbase account so that the mining reward goes to this account. This can be achieved using the following command. Currently, the Ether-based account has no balance, as can be seen by using the following command. In this section, we created a private network with a custom Genesis file. Also, we created a new account in our private network. Now we are ready to start mining on our private network. Mining on the private network. Now that we have started up our private network, mining can start by simply issuing the following command. This command takes one parameter, the number of threads. In the following example, 2 threads will be allocated to the mining process by specifying 2 as an argument to the start function. After the preceding command is issued as preparation for mining, the DAG generation process starts, which produces an output similar to the one shown here. DAG stands for Directed Acyclic Graph. We briefly introduced this when discussing ethash in Chapter 12, Further Ethereum. In the context of Ethereum's ethash POW algorithm, DAG refers to Dagger, which is a memory-hard POW algorithm based on moderately connected directed acyclic graphs. The aim of the Dagger algorithm is to provide an ASIC-resistant memory-hard POW algorithm. The Dagger algorithm works by generating a DAG of a few gigabytes every 30,000 blocks. This DAG serves as a resource for POW where the POW mechanism needs to choose subsets from the DAG, which is dependent on the nonce and the block header. This is in contrast to Bitcoin POW, which is based on calculating SHA-256, which is not resistant to specialized hardware, such as ASICs. Once DAG generation is finished, the mining process starts and blocks are produced. Geth will produce an output similar to that shown in the following. It can be seen that blocks are being mined successfully with the mine potential block message. Mining can be stopped using the following command. Now, before the further exploration of different methods, let's understand some basics of using the JavaScript console. In the JavaScript console, we can perform several operations. A general tip is that if 2 spaces and 2 tabs on the keyboard are pressed in a sequence, a complete list of the available objects will be displayed. This is shown in the following screenshot. Furthermore, when a command is typed, it can be auto-completed by pressing tab twice. If 2 tabs are pressed, then the list of available methods is also displayed. This is shown in the following screenshot. In addition to the previously mentioned command, in order to get a list of available methods of an object after typing a command, a semicolon is entered. An example is shown in the next screenshot, which shows a list of all the methods available for net. There is also the ETH object available, which has several methods. While there are several methods under this object, the most common is getBalance, which we can use to query the current balance of Ether. This is shown in the following example. After mining, a significant amount can be seen here. Mining is extremely fast as it is a private network with no competition for solving the POW. and also in the Genesis file, the network difficulty has been set to quite low. The preceding balance is shown in Way. If we want to see the output in Ether, we can use the Web3 object as shown here. There are a few other commands that can be used to query the private network. Some examples are shown as follows. Get the current gas price. Get the latest block number. Debug can come in handy when debugging issues. A sample command is shown here. However, there are many other methods available. A list of these methods can be viewed by typing debug. The following method will return the RLP of block 0. The preceding output shows the block 0 in RLP encoded format. Create a new account. Note that password 123 is the password chosen as an example, but you can choose any. Unlock the account before sending transactions. We use allow unsecure unlocking, otherwise the accounts cannot be unlocked with HTTP access. If that is the case, you will see an error message as follows. To circumvent the error, restart Geth using the -allow -insecure-unlock flag. Now we unlock both accounts that we created earlier with the personal.newAccount command at the start of the private network we're creating, and just before the unlock account command on this page. The first account we created at the start of our private network is 0xC9BF762718888E0F52351BD B65811, and another 0xD6E364A137E8F528DDBAD2BB235-6D124C9A08206, just at the start of this page. Now, once we have these accounts unlocked, we can issue some further command to query the balances they hold. First, let's check the balance of our account that we created earlier when we started our private network the first time. At this account is also our Coinbase account, which is the default account that receives the mining reward. We can also query the balance slightly differently by specifying eth.coinbase in the command, as shown here. Finally, we check the balance of the other account that we created. As this has not received any mining reward, the balance is 0 as expected. Now let's try to send transactions from one account to another. In this example, we'll send Ether from account 0xC9BF7627 1B9E4 2E4 BF7E18888E0F5235 1BD B65811 to 0xD6E364A137E8F528 DDBAD2BB235 6D124C9A08206, using the send transaction commands shown as follows. First, we send the value of 100. This command outputs the transaction hash, which is a unique identifier used to identify a specific transaction. The output is shown as follows. This command will transfer 100 Way, the smallest Ether unit, to the target account. To transfer the value in Ether, in our example 100 Ether, we can use the command slightly differently and use web3.toWay, which will convert the value from Ether into Way. To achieve this, we issue the command as shown here. This command outputs the transaction hash as shown here. The preceding command makes use of web3.toWay, which takes two parameters, value which is 100 in our example, and a string Ether which is the unit of value. This means that 100 Ether will be converted into its equivalent Way and will be used in the send transaction command. The result of this command will be transferring 100 Ether from our source account to the target account. Also notice in the logs in the other console terminal window from where we ran the geth command to run our private network earlier at the start of the private network, the log message. This message shows that the transaction has been submitted, but it needs to be mined first in order for the transaction to take effect. As we stopped mining earlier, for this transaction to go through, we need to start mining again. Otherwise, the transaction won't be processed. Now check in the logs that the mining has started to work. Note that the amount of funds has been transferred. It could be a bit cumbersome to type all these account IDs. Instead of typing these long account IDs, we can also use the list accounts method, which takes an integer parameter to address the account. For example, 0, which represents the first account that we created. As list accounts returns all the account addresses of all the keys in the key store, by providing 0 as a parameter, we can refer to the first account that we created. Now let's see an example of using the list accounts method as shown here. We can also now query information about the transaction that we executed earlier. Remember how it returned a transaction hash? We can use that to find out details about the transaction. This will produce the output shown as follows. Notice the root in the preceding output, the transaction root, which will be available in the block header as the Merkle root of the transaction tree. Similarly, we can query more information about the transaction using the getTransaction method. This will produce the output shown as follows. In this section, we covered how to start mining on a private network and ran some transactions. We also saw how transactions can be created and balance can be queried and performed an Ether transfer transaction from one account to another. We also covered how the transaction results can be queried using a transaction receipt and other relevant methods available via RPC in the Geth client. We've seen in the examples previously that there is a rich interface available with hundreds of methods to interact with the blockchain. While this console terminal-based mechanism is quite useful, it can become a bit difficult to manage and deploy smart contracts using the command line console. For this, we need better alternatives, which we will discuss next. Just like any other development ecosystem in IT, the Ethereum ecosystem has come a long way toward providing high-quality and user-friendly development tools. We will introduce some of these in the next section. Remix IDE. There are various integrated development environments, IDEs, available for Solidity development. Most of the IDEs are available online and are presented via web interfaces. Remix, formerly Browser Solidity, is the most commonly used IDE for building and debugging smart contracts. It is discussed here. Remix is the web-based environment for the development and testing of contracts using Solidity. It is a feature-rich IDE that does not run on a live blockchain. In fact, it is a simulated environment in which contracts can be deployed, tested, and debugged. It is available at remix.ethereum.org. An example interface is shown as follows. On the left-hand side, there is a column with different icons. These icons represent various plugins of the Remix IDE. When you run Remix for the first time, it won't show any of the plugins. In order to add plugins to Remix IDE, you need to access the plugin manager to activate the plugins you need. This is shown in the following figure. There are a number of plugins available. A sample screenshot is shown here. Once activated, the plugins will appear in the leftmost column of the IDE, as shown in the following image. Again, note that this will only show the plugins that are activated, and other plugins or local plugins can be activated as required. The following screenshot provides more details of different elements of the Remix IDE. On the right-hand side, there is a code editor with syntax highlighting and code formatting. And on the left-hand side, there are a number of plugins available that can be used to deploy, debug, test, and interact with the contract. Various features such as transaction interaction, options to connect to the JavaScript VM, the configuration of an execution environment, debugger, formal verification, and static analysis are available. They can be configured to connect to execution environments such as the JavaScript VM injected Web3, where Mist, MetaMask, or a similar environment has provided the execution environment, or the Web3 provider, which allows connection to the locally running Ethereum client. For example, Geth, via IPC or RPC over HTTP, Web3 provider endpoint. Remix also has a debugger plugin for EVM that is very powerful and can be used to perform detailed level tracing and analysis for the EVM of the EVM bytecode. An example is shown here. The preceding screenshot shows different elements of the Remix IDE when debugger is running. On the right-hand side, the source code is shown. Below that is the output log, which shows informational messages and data related to compilation and the execution status and transaction information of the transaction contract. The following screenshot shows the Remix debugger in more detail. It has the source code decoded into EVM instructions. The user can step through the instructions one by one and examine what the source code does when executed. Note that in the preceding screenshot, the opcodes are displayed along with memory, state, and stack information. Notice that solidity state has a value of 10 assigned to the variable x after the execution of the transaction. There are also a number of other related information points shown in the debugger. This is a very useful feature and comes in handy, especially in complex code debugging. In the next section, we'll be using MetaMask, a browser extension that serves as a cryptocurrency wallet and an interface to blockchains and dApps. MetaMask. MetaMask allows interaction with Ethereum blockchain via the Firefox and Chrome browsers. It injects a Web3 object within the running website's JavaScript context, which allows immediate interface capability for dApps. This injection allows dApps to interact directly with the blockchain. MetaMask also allows account management. This acts as a verification method before any transaction is executed on the blockchain. The user is shown a secure interface to review the transaction for approval or rejection before it can reach the target blockchain. It allows connectivity with various Ethereum networks as shown in the following screenshot. This is a screenshot of the MetaMask user interface, where it allows users to select the network of their choice. An interesting feature to note is that MetaMask can connect to any Ethereum blockchain via the custom RPC connection. It can connect to not only remote blockchains but also to locally running blockchains. All it needs is an RPC connection exposed by a node running on the blockchain. If it's available, MetaMask can connect and will allow a web browser to connect to it via the Web3 object. MetaMask can also be used to connect to a locally running test or simulated blockchain like Ganache and Test RPC. MetaMask allows account management and also records all transactions for these accounts. This is shown in the following screenshot. As we now understand what MetaMask is, we can now delve deeper and see how the Remix IDE can deploy smart contracts through MetaMask. Using MetaMask and Remix IDE to deploy a smart contract. MetaMask was introduced in Chapter 12, Further Ethereum. It is an interface between the Ethereum blockchain and the web browser. It enables easy access to the blockchain and is quite useful for development activities. As MetaMask injects a Web3 object into the browser, we can use it with Remix IDE to deploy contracts to the blockchain. It is very easy to deploy new contracts using MetaMask and Remix. Remix IDE provides an interface where contracts can be written in Solidity and then deployed on the blockchain. We will use Remix IDE and MetaMask to deploy a sample smart contract to the local running private blockchain that we just created in the last section. In the exercise, a simple contract that can perform various simple arithmetic calculations on the input parameter will be used. As we have not yet introduced Solidity, the aim here is to demonstrate the contract deployment and interaction process only. More information on coding and Solidity will be provided later in Chapter 14, Development Tools and Frameworks, and Chapter 15, Introducing Web3, after which the following code will become easy to understand. Those of you who are already familiar with JavaScript or any other similar language such as the C language will find the code almost self-explanatory. Now let's look at some examples of how MetaMask can be used in practice with the private net that we have created earlier in this chapter, adding a custom network to MetaMask and connecting Remix IDE with MetaMask. First, ensure that you have MetaMask available as we set it up in Chapter 12, Further Ethereum. If not, you can refer back to the previous chapter for an installation guide. In this section, we will add our local private network in MetaMask, and then interact with it using Remix IDE. Open the Google Chrome browser, where MetaMask is installed. Select localhost 8545, where the Geth instant of our private net is listening on. Navigate to Remix IDE for Ethereum smart contract development on your browser at https://remix.ethereum.org. Once on the website, notice the Deploy and Run Transactions option in the left-hand column. Choose Injected Web3 as the environment. This is shown in the following screenshot on the left-hand side. A MetaMask window will open as shown in the preceding screenshot. On the right-hand side, note that when Remix IDE is connected to MetaMask, it will show network information such as custom 786 network and account information as shown in the following screenshot. In this section, we saw how Remix can connect to MetaMask using the Injected Web3 environment. MetaMask can be connected to the mainnet or any other network, local or test network. But from Remix's point of view, as long as the Injected Web3 object is available, it will connect to it. In our example, as we are using a private net, we have connected to our private network through MetaMask, and Remix is connecting to MetaMask using the Injected Web3 environment. Now, even if we have this connectivity available, MetaMask does not know about the accounts that we have created in our private network. In order for MetaMask to operate on existing accounts, we need to import them from the existing key store, in our case, the private network 786 key store. We will see how this is done in the next section, importing accounts into MetaMask using key store files. We can import existing Ethereum accounts into MetaMask by importing the key store files generated by Geth as a result of creating accounts. To demonstrate how this works, we will now import the accounts from our private network blockchain, named 786, into MetaMask. In MetaMask, the Import Account option is available under the My Accounts menu, as shown in the following screenshot. Now let's import the accounts. Remember, we created 2 accounts earlier in our private network 786. We can import these accounts into MetaMask using their associated keystore JSON files. The steps are as follows. The keystore files for our private net are listed here. Simply browse to the keystore and select the keystore file, then enter the password earlier when we created the accounts for the first time. We set the password as password123 and click Import. It may take a few seconds to import. When imported, the account will be visible in the MetaMask window as shown here. Similarly, we can import the other account by selecting the keystore file and importing it. Finally, we will have 2 accounts listed in MetaMask, as shown in the following image. Now that our accounts have been imported successfully, we can move on to using MetaMask to deploy a contract in our private network. Deploying a contract with MetaMask. In this section, we will write a simple smart contract and deploy it on our private network using MetaMask. First, in Remix, we create a new file. Enter the code shown for Simple Contract 2. The code will look like this in Remix. Now we compile the smart contract 2 by clicking on the Compile Simple Contract 2.sol button, as shown here. Once compiled successfully, we deploy the smart contract in the private net. When we click Deploy, the following window is displayed, shown on the left-hand side. Also, in the Data tab, you can see the contract code, shown on the right-hand side. Notice how in the Geth logs we see Submitted Contract Creation, which means that a contract creation transaction has been submitted and acknowledged as a result of the deploy action from the Remix IDE and the confirm action from MetaMask. Note that it also shows the full hash and contract address. Now we start mining again by issuing the following command in the JavaScript console of Geth. If mining is already running, this step is not required. Once the contract is mined and deployed, you can see it in Remix under the Deployed Contracts view. With this, we have successfully deployed our sample smart contract on the private network. Next, we'll see how we can interact with this contract using Remix IDE and MetaMask. Interacting with a contract through MetaMask using Remix IDE. Now we can interact with the contract using MetaMask. We run the addition option, enter a value of 100 in the box, and click on the Addition button, as shown in the following screenshot on the left-hand side. This will invoke the MetaMask window, as shown in the following screenshot on the right-hand side. Click Confirm and the transaction will be mined as usual because we have a miner running the background in Geth. Now click on the Cur Value button, which will read the contract to find the current value, which is, as expected, 105. This value is the result of the addition operation being performed. Recall that we provided a value of 100 and in the smart contract we have already hard-coded 5 in the addition function, as shown here. This means that 100 provided by us as input is added to 5, which is hard-coded in the smart contract addition function, and the result of this calculation is 105, as expected. This is a very simple program, but the aim of this exercise is to demonstrate the use of MetaMask and how it can connect with the local private chain using the localhost RPC provider running in Geth on port 8545. Pay special attention to the Solidity compiler settings, choose the appropriate compiler version, and the EVM version according to your source code and your Geth client's EVM version. If this is not selected appropriately, you can run into issues. For example, if an incorrect version of EVM, as shown in the following screenshot, is chosen, then when interacting with the contract, you may see the error message shown in the second screenshot with the caption, "Gas estimation failed error." Similarly, if an incorrect EVM version is chosen, then you will also see an error message in the Remix window, as shown in the following screenshot. It's best to configure the settings correctly, which can be left as defaults in most cases, unless there are specific features of an EVM version that you are testing. Compiling for the wrong version of the EVM can result in incorrect and failing behavior. For example, if you have chosen the EVM version as Petersburg, as shown in figure 13.38, and you've used some opcodes that were introduced in Istanbul, a later release, then even if the compilation is successful, the bytecode at runtime will fail to run correctly and will report an error saying that the opcode is invalid. In some other cases, the runtime may even fail silently or with little indication in the Geth logs about what happened, leading to hours of wasted time in debugging. This is especially true in private networks. Therefore, make sure that the correct EVM version that matches with the Geth client release is used. Also, notice in the following screenshot that the compiler version is set to 0.5.0 automatically. This is due to the compiler version specified in Solidity source code as 0.5.0 in the line Pragma Solidity 0.5.0. Also notice the EVM version, which is set to default, which is the latest EVM release. In the MetaMask view, you can also see the transaction history of the contract. The preceding diagram shows a number of different elements. On the left-hand side, we have the Deploy and Run Transactions window, which is part of the Remix IDE. The middle window is where we see the contract source code. The window just below that is a log window where the result of the transactions and any interaction and results are shown. It can also optionally listen to the network, if Listen on Network is selected. On the right-hand side, we have the MetaMask windows, which is not part of the Remix IDE, but is just superimposed on top of the Remix IDE to show the MetaMask transaction history. Another way to connect to the local private net Geth node is to directly connect using the Web3 provider. This will allow direct communication with the blockchain through Remix via RPC without requiring an injected Web3 environment. One advantage of this method is that it is a quick and easy method to connect Remix with the underlying blockchain Geth node. There is no need for additional tools. All you need is Remix IDE, which is also browser-based, and your local running Geth node. The disadvantage, however, is that this method is not very secure. This can be achieved using the following option, available in Remix. Notice in the preceding screenshot that environment is set to Web3 provider, which simply connects to localhost:8545. Notice that our Geth process is running with the required parameters already, which allows Web3 provider connection, as shown here. Notice that in the preceding command we have the --rpc ors domain flag set. If we didn't have this flag set, then the only option would have been to connect via injected Web3, which in fact is a more secure way to connect to the chain using MetaMask. As such, we use that as a standard, but if you have a simple local test network, you can always use the Web3 provider option to quickly interact with the blockchain using Remix IDE. Using the flag --rpc ors domain with the wildcard --rpc ors domain asterisk is not advisable. Using the wildcard asterisk will allow everyone to connect to the node. Therefore, it is recommended that the access is restricted by specifying only trusted URLs. For example, --rpc ors domain remix.ethereum.org. However, --rpc ors domain with the wildcard asterisk can be used with a local test chain with test accounts. Always specify the URL in the case of real accounts or on the mainnet. Now we can stop the miner. With this example, we have now covered how MetaMask can be used to connect to the local network, and how Remix and MetaMask, or only Remix, can be used to connect to the local network and deploy smart contracts. We also saw how to interact with a deployed contract. Remix is a very feature-rich IDE, and we have not covered everything. However, this chapter has included a formal introduction to Remix, describing most of the main features in detail, and we will keep using it in the chapters to come. It is also useful to have a mechanism to view a consolidated list and details of all the transactions in the blockchain. For this purpose, block explorers are used. There are many services available for public blockchains on the internet. For more details on how to use a local block explorer, go to the companion website of this book at static.pact-cd_ethereum_projects_and_more_bonus_content.pdf. Summary. In this chapter, we have explored Ethereum test networks and how to set up private Ethereum networks. After the initial introduction to private network setup, we also saw how the Geth command line tool can be used to perform various functions, and how we can interact with the Ethereum blockchain. We also saw how MetaMask and Remix can be used to deploy smart contracts. We also introduced how block explorers play a vital role in monitoring the blockchain networks, and saw a basic example of installing and using an open-source block explorer. In the next chapter, we will see in greater detail what tools, programming languages, and frameworks are available for the development of smart contracts on Ethereum. Chapter 14: Development Tools and Frameworks. This chapter is an introduction to the development tools, languages, and frameworks used for Ethereum smart contract development. We will examine different methods of developing smart contracts for the Ethereum blockchain. We will discuss various constructs of the Solidity language in detail, which is currently the most popular development language for smart contract development on Ethereum. In this chapter, we will cover the following topics: languages, compilers, tools and libraries, frameworks, contract development and deployment, the layout of a Solidity source code file, the Solidity language. There are a number of tools available for Ethereum development. The following diagram shows the taxonomy of various development tools, clients, IDEs, and development frameworks for Ethereum. The preceding taxonomy does not include all frameworks and tools that are out there for development on Ethereum. It shows the most commonly used tools and frameworks, including some that we will use in our examples throughout this chapter. Since we have discussed some of the main tools available in Ethereum in previous chapters, such as the Remix IDE and MetaMask, this chapter will focus mainly on Geth, Solidity, Ganache, Sulk, and Truffle. Some other elements such as prerequisites, Node.js, will also be discussed briefly. We'll start by exploring some of the programming languages that can be used in the Ethereum blockchain. Languages. Smart contracts can be programmed in a variety of languages for the Ethereum blockchain. There are 6 main languages that can be used to write contracts. Solidity. This language has now become almost a standard for contract writing for Ethereum. This language is the focus of this chapter and is discussed in detail in later sections. Viper. This language is a Python-like experimental language that is being developed to bring security, simplicity, and auditability to smart contract development. Yule. This is an intermediate language that has the ability to compile to different backends such as EVM and eWASM. The design goals of Yule mainly include readability, easy control flow, optimization, formal verification, and simplicity. Mutan. This is a Go-style language which was deprecated in early 2015 and is no longer used. LLL. This is a low-level Lisp-like language, hence the name LLL. This is also no longer used. Serpent. This is a simple and clean Python-like language. It is not used for contract development anymore and is not supported by the community. As Solidity code needs to be compiled into bytecode, we need a compiler to do so. In the next section, we will introduce the Solidity compiler. Compilers. Compilers are used to convert high-level contract source code into the format that the Ethereum execution environment understands. The Solidity compiler, Sulk, is the most common one in use, which is discussed next. The Solidity compiler. Sulk converts from a high-level Solidity language into Ethereum Virtual Machine, EVM, bytecode so that it can be executed on the blockchain by the EVM. Installation. Sulk can be installed on a Linux Ubuntu operating system using the following commands. $sudo apt-get install sulk. If personal package archives, PPAs, are not already installed, those can be installed by running the following commands. To install Sulk on Mac OS, execute the following commands. $brew tap Ethereum/Ethereum. This command will add the Ethereum repository to the list of brew formulas. $brew install Solidity. This command will produce a long output and may take a few minutes to complete. If there are no errors produced, then eventually it will install Solidity. In order to verify that Solidity compiler is installed and to validate the version of the compiler, the following command can be used. $sulk-version. This command will produce the output shown as follows, displaying the version of the Solidity compiler. This output confirms that the Solidity compiler is installed successfully. Functions. Sulk supports a variety of functions. A few examples are shown as follows. As an example, we'll use a simple contract, addition.sol, displaying the contract in a binary format. In order to see the smart contract in compiled binary format, we can use the following command. $sulk-bin addition.sol. This command will produce an output similar to the following. This output shows the binary translation of the addition.sol contract code represented in hex. Estimating gas. As a gas fee is charged for every operation that the EVM executes, it's a good practice to estimate gas before deploying a contract on a live network. Estimating gas gives a good approximation of how much gas will be consumed by the operation specified in the contract code. which gives an indication of how much ether is required to be spent in order to run a contract. We can use the -- gas flag for this purpose, as shown in the following example. $soak -- gas addition.sol. This will give the following output. This output shows how much gas usage is expected for these operations in the addition.sol smart contract. The gas estimation is shown next to each function. For example, the ADDX function is expected to use 21,120 gas. Generating the ABI. We can generate the application binary interface, ABI, using Sulk, which is a standard way to interact with the contracts. $soak -- ABI addition.sol. This command will produce a file named addition.abi as output. The following are the contents of the output file addition.abi. The preceding output displays the contents of the addition.abi file, which are formatted in JSON style. It consists of inputs and outputs along with their types. We will generate and use ABIs later in this chapter to interact with the deployed smart contracts. Compilation. Another useful command to compile and produce a binary compiled file along with an ABI is shown here. The message displays if the compiler run is successful, otherwise errors are reported. This command will produce a message and two files in the output directory bin. Addition.abi. This file contains the ABI of the smart contract in JSON format. Addition.bin. This contains the hex representation of binary of the smart contract code. The output of both files is shown in the following screenshot. Sulk is a very powerful command, and further options can be explored using the -- help flag, which will display detailed options. However, the preceding commands used for compilation, ABI generation, and gas estimation should be sufficient for most development and deployment requirements. Tools and libraries. There are various tools and libraries available for Ethereum. The most common ones are discussed here. In this section, we will first install the prerequisites that are required for developing applications for Ethereum. The first requirement is Node.js, which we'll install next. Node.js. As Node.js is required for most of the tools and libraries, it can be installed using the following commands. Node.js can either be installed directly from the website or by using bash. Alternatively, Node.js can be installed using Brew on Mac OS. Or go to nodejs.org/en/download and install Node.js for your operating system, as shown in the following screenshot. Ganache CLI. At times, it is not possible to test on the testnet, and the mainnet is obviously not a place to test contracts. A private network can be time-consuming to set up at times. Ganache CLI, formerly Ethereum.js, comes in handy when quick testing is required and no testnet is available. It stimulates the Ethereum Geth client behavior and allows faster development testing. Ganache CLI is available via npm as a node.js package. Before installing test RPC, node.js should already have been installed and the npm package manager should also be available. Ganache-CLI can be installed using this command. In order to start Ganache-CLI, simply issue this command. Keep it running in the background and open another terminal to work on contracts. When test RPC runs, it will display an output similar to the one shown in the following screenshot. It will automatically generate 10 accounts and private keys, along with an HD wallet. It will start to listen for incoming connections on TC port 8545. Ganache-CLI has a number of flags to customize the stimulated chain according to your requirements. For example, flag-A allows you to specify the number of accounts to generate at startup. Similarly, -B allows the user to configure block time for mining. Detailed help is available using the following command. Ganache CLI is a command line tool. However, at times it is desirable to have a fully featured tool with a rich graphical user interface, GUI. A GUI equivalent of Ganache CLI is Ganache, which we will introduce next. Ganache. Ganache is a notable addition to the ever-growing set of development tools and libraries developed for Ethereum. This is a simulated personal blockchain with a user-friendly GUI to view transactions, blocks, and relevant details. This is a fully working personal blockchain that supports the simulation of a number of different hard forks, such as Homestead, Byzantium, Istanbul, or Petersburg. Ganache is based on a JavaScript implementation of the Ethereum blockchain, with built-in block explorer and mining, making testing locally on the system very easy. As shown in the following screenshot, you can view transactions, blocks, and addresses in detail on the front end. When you start Ganache for the first time, it will ask whether the user wants to create a quick blockchain or create a new workspace that can be saved. And it also has advanced setup options. Select the New Workspace or Quick Start option as required. We will choose New Workspace as we want to explore more advanced features. For a quicker temporary setup with default options, which could be useful for simple testing, you can choose Quick Start. If New Workspace is selected, there are a number of options available to configure the blockchain. The configuration options are Workspace Name, where you can specify a name for your project. Additionally, Truffle projects can also be added here. We will cover Truffle in more detail later in the chapter. Other options include Server, Accounts and Keys, Chain, and Advanced. The Server tab is used to configure RPC connectivity by specifying the hostname, port number, and network ID. Accounts and Keys provides options to configure balance and the number of accounts to generate. The Chain option provides a configuration interface for specifying the gas limit, gas price, and hard fork, which is required to be simulated, such as Byzantine or Petersburg. The Advanced option is available to configure logging and analytics-related settings. Once you have all the configuration options set, save the workspace by selecting Save Workspace, and the main transaction view of the Ganache personal blockchain will show. With this, we conclude our introduction to Ganache, a mainstream tool used in blockchain development. Now we will move on to different development frameworks that are available for Ethereum. Frameworks. There are a number of other notable frameworks available for Ethereum development. It is almost impossible to cover all of them, but an introduction to some of the mainstream frameworks and tools is given as follows. Truffle. Truffle, available at trufflesuite.com, is a development environment that makes it easier and simpler to test and deploy Ethereum contracts. Truffle provides contract compilation and linking along with an automated testing framework using Mocha and Kai. It also makes it easier to deploy the contracts to any private net, public, or testnet Ethereum blockchain. Also, an asset pipeline is provided, which makes it easier for all JavaScript files to be processed, making them ready for use by a browser. Before installation, it is assumed that Node is available, which can be queried as shown here. If Node is not available, then the installation of Node is required first in order to install Truffle. The installation of Truffle is very simple and can be done using the following command via Node Package Manager, npm. $npm install truffle-g. This will take a few minutes. Once it is installed, the Truffle command can be used to display help information and verify that it is installed correctly. Type Truffle in the terminal to display usage help. This will display the following output. Alternatively, the repository is available at github.com/trufflesuite/truffle, which can be cloned locally to install Truffle. Git can be used to clone the repository using the following command. $git clone We will use Truffle later in Chapter 15, Introducing Web3, to test and deploy smart contracts on the Ethereum blockchain. For now, we'll continue to explore some of the frameworks used for development on the Ethereum blockchain. Drizzle, Web User Interface UI development, is an important part of the app development. As such, many web techniques and tools, ranging from simple HTML and JavaScript to advanced frameworks such as Redux and React, are used to develop web UIs for the apps. We will cover basic JavaScript and HTML-based UIs along with an advanced framework called Drizzle in the upcoming chapters. Drizzle is a collection of front-end libraries that allows the easy development of web UIs for decentralized applications. It is based on the Redux store and allows seamless synchronization of contract and transaction data. Drizzle is installed using the following command: $npm install drizzle-save. In Chapter 15, Introducing Web3, we will explore Drizzle in detail and use it in some examples. Embark. Embark is a complete and powerful developer platform for building and deploying decentralization applications. It is used for smart contract development, configuration, testing, and deployment. It also integrates with Swarm, IPFS, and Whisper. There is also a web interface called Cockpit available with Embark, which provides an integrated development environment for easy development and debugging of decentralized applications. Embark can be installed by using the following command: $npm install -g embark. More details on Embark are available on the official website at framework.embarklabs.io. Brownie. Brownie is a Python-based framework for Ethereum smart contract development and testing. It has the full support of Solidity and Viper with relevant testing and debugging tools. More information is available at eth-brownie.readthedocs.io/en/stable. Waffle. Waffle is a framework for smart contract development and testing. It is claimed to be faster than Truffle. More details are available on the official website at getwaffle.io. Etherlime. This framework allows the app development, debugging, testing, and testing in Solidity and Viper. It is based on ether.js. github.com/ethers-io/ethers.js. OpenZeppelin. This toolkit has a rich set of tools that allow easy smart contract development. It supports compiling, deploying, upgrading, and interacting with smart contracts. Further information is available here, openzeppelin.com/SDK. In this section, we have covered some of the mainstream frameworks that are used in the Ethereum ecosystem for development. In the next section, we will explore which tools are available for writing and deploying smart contracts. Contract development and deployment. There are various steps that need to be taken in order to develop and deploy the contracts. Broadly, these can be divided into 3 steps: writing, testing, and deployment. After deployment, the next optional step is to create the UI and present it to the end users via a web server. A web interface is sometimes not needed in the contracts where no human input or monitoring is required. But usually there is a requirement to create a web interface so that the end users can interact with the contract using familiar web-based interfaces. Writing smart contracts. The writing step is concerned with writing the contract source code in Solidity. This can be done in any text editor. There are various plugins and add-ons available for Vim in Linux, Atom, and other editors that provide syntax highlighting and formatting for Solidity source code. Visual Studio Code has become quite popular and is used commonly for Solidity development. There is a Solidity plugin available that allows syntax highlighting, formatting, and IntelliSense. It can be installed via the extensions option in Visual Studio Code. The preceding screenshot displays a Visual Studio Code window that comprises a file explorer on the left-hand side, and a code editor window. Due to syntax highlighting and IntelliSense being enabled by the Solidity plugin, it becomes easy to write smart contract code. The Solidity plugin for Visual Studio is available in the Visual Studio Marketplace. Testing smart contracts. Testing is usually performed by automated means. Earlier in the chapter, you were introduced to Truffle, which uses the Mocha framework to test contracts. However, manual functional testing can be performed as well by using the Remix IDE, which was discussed in Chapter 13, Ethereum Development Environment, and running functions manually and validating results. We will cover this in Chapter 15, Introducing Web3. Deploying smart contracts. Once the contract is verified, working, and tested on a simulated environment, for example Ganache, or on a private net, it can be deployed to a public testnet such as Ropsten, and eventually to the live blockchain, mainnet. We will cover all these steps including verification, development, and creating a web interface in the next chapter, Chapter 15, Introducing Web3. Now that we have covered which tools can be used to write Solidity smart contracts, we will introduce the Solidity language. This will be a brief introduction to Solidity, which could provide the base knowledge required to write smart contracts. The syntax of the language is very similar to C and JavaScript, and it is quite easy to program. We'll start by exploring what a smart contract written in the Solidity language looks like. The layout of a Solidity source code file. In the following subsections, we will look at the components of a Solidity source code file, which is important to cover before we move on to writing smart contracts in the next section. Version Pragma. In order to address compatibility issues that may arise from future versions of the Sulk version, Pragma can be used to specify the version of the compatible compiler, as in the following example. This will ensure that the source file does not compile with versions lower than 0.5.0 and versions starting from 0.6.0. Import. Import in Solidity allows the importing of symbols from the existing Solidity files into the current global scope. This is similar to import statements available in JavaScript, as in the following, for example. Comments. Comments can be added to the Solidity source code file in a manner similar to the C language. Multiple line comments are enclosed in \*** and ***, whereas single line comments start with \***. An example Solidity program is as follows, showing the use of Pragma, import, and comments. In this section, we examine what Solidity code of a smart contract looks like. Now it's time to learn about the Solidity language. The Solidity language. Solidity is a domain-specific language of choice for programming contracts in Ethereum. There are other languages that can be used, such as Serpent, Muton, and LLL. But Solidity is the most popular. Its syntax is closer to both JavaScript and C. Solidity has evolved into a mature language over the last few years and is quite easy to use, but it still has a long way to go before it can become advanced, standardized, and feature-rich like other well-established languages such as Java, C, or C#. Nevertheless, this is the most widely used language currently available for programming contracts. It is a statically typed language, which means that variable type checking in Solidity is carried out at compile time. Each variable, either state or local, must be specified with a type at compile time. This is beneficial in the sense that any validation and checking is completed at compile time, and certain types of bugs, such as the interpretation of data types, can be caught earlier in the development cycle instead of at runtime, which could be costly, especially in the case of the blockchain smart contract paradigm. Other features of the language include inheritance, libraries, and the ability to define composite data types. Solidity is also called a contract-oriented language, In Solidity, contracts are equivalent to the concept of classes in other object-oriented programming languages. Variables. Just like any programming language, variables in Solidity are named memory locations that hold values in a program. There are three types of variables in Solidity: local variables, global variables, and state variables. Local variables. These variables have a scope limited to only within the function they are declared in. In other words, their values are present only during the execution of the function in which they are declared. Global variables. These variables are available globally as they exist in the global namespace. They are used for performing functions such as ABI encoding, cryptographic functions, and querying blockchain and transaction information. Solidity provides a number of global variables that are always available in the global namespace. These variables provide information about blocks and transactions. Additionally, cryptographic functions, ABI encoding, decoding, and address-related variables are available. A subset of available variables is shown as follows. This function is used to compute the CAC 256 hash of the argument provided to the function. This function returns the associated address of the public key from the elliptic curve signature. This returns the current block number. This returns the gas price of the transaction. State variables. State variables have their values permanently stored in smart contract storage. State variables are declared outside the body of a function, and they remain available throughout the contract depending on the accessibility assigned to them and as long as the contract persists. Here, X is a state variable whose value will be stored in contract storage. There are three types of state variables, based on their visibility scope. Private. These variables are only accessible internally from within the contract that they are originally defined in. They are also not accessible from any derived contract from the original contract. Public. These variables are part of the contract interface. In simple words, anyone is able to get the value of these variables. They are accessible within the contract internally by using the this keyword. They can also be called from other contracts and transactions. A getter function is automatically created for all public variables. Internal. These variables are only accessible internally within the contract that they are defined in. In contrast to private state variables, they are also accessible from any derived contract from the original parent contract. In the next section, we will introduce the data types supported in Solidity. Data types. Solidity has two categories of data types: value types and reference types. Value types are variables that are always passed by a value. This means that value types hold their value or data directly, allowing a variable's value held in memory to be directly accessible by accessing the variable. Reference types store the address of the memory location where the value is stored. This is in contrast with value types, which store the actual value of a variable directly with the variable itself. When using reference types, it is essential to explicitly specify the storage area where the type is stored. For example, memory, storage, or call data. The specific location used for storing values of a variable depends on the data type of the variable and where the variable has been declared. For example, function parameter variables are stored in memory, whereas state variables are stored in storage. Now we'll describe value types in detail. Value types. Value types mainly include booleans, integers, addresses, and literals, which are explained in detail here. Boolean. This type has two possible values, true or false, for example. This statement assigns the value true or false to v depending on the assignment. Integers. This data type represents integers. The following table shows various keywords used to declare integer data types. For example, in this code, note that unit is an alias for unit 256. These types can also be declared with the constant keyword, which means that no storage slot will be reserved by the compiler for these variables. In this case, each occurrence will be replaced with the actual value. Address. This data type holds a 160-bit long, 20-byte value. This type has several members that can be used to interact with and query the contracts. These members are described here. Balance. The balance member returns the balance of the address in way. Send. This member is used to send an amount of Ether to an address, Ethereum's 160-bit address, and returns true or false depending on the result of the transaction. For example, the following. Call functions. The call code, and delegate call functions are provided in order to interact with functions that do not have an ABI. These functions should be used with caution, as they are not safe to use due to the impact on type safety and security of the contracts. Array value types, fixed size and dynamically sized byte arrays. Solidity has fixed sized and dynamically sized byte arrays. Fixed size keywords range from bytes 1 to bytes 32, whereas dynamically sized keywords include bytes and string. The bytes keyword is used for raw byte data, and string is used for strings encoded in UTF-8. As these arrays are returned by the value, calling them will incur a gas cost. Length is a member of array value types and returns the length of the byte array. An example of a static fixed size array is as follows. An example of a dynamically sized array is as follows. Get the length of trades by using the following code. Literals. These are used to represent a fixed value. There are different types of literals that are described as follows. Integer literals. These are a sequence of decimal numbers in the range of 0 to 9. An example is shown as follows. String literals. This type specifies a set of characters written with double or single quotes. An example is shown as follows. Hexadecimal literals. These are prefixed with the keyword hex and specified within double or single quotation marks. An example is shown as follows. Enums. This allows the creation of user-defined types. An example is shown as follows. Explicit conversion to and from all integer types is allowed with enums. Reference types. As the name suggests, these types are passed by reference and are discussed in the following section. These are also known as complex types. Reference types include arrays, structs, and mappings. Arrays. Arrays represent a contiguous set of elements of the same size and type laid out at a memory location. The concept is the same as any other programming language. Arrays have two members, named length and push. Structs. These constructs can be used to group a set of dissimilar data types under a logical group. These can be used to define new custom types, as shown in the following example. In the preceding code, we declared a struct named trade that has 4 fields. Trade ID, quantity, and price are of the uint type, whereas trader is of the string type. Once the struct is declared, we can initialize and use it. We initialize it by using trade tstruct and assigning 123 to trade ID, 1 to quantity, and equinox to trader. Data location. Sometimes it is desirable to choose the location of the variable data storage. This choice allows for better gas expense management. We can use the data location name to specify where a particular complex data type will be stored. Depending on the default or annotation specified, the location can be storage, memory, or call data. This is applicable to arrays and structs and can be specified using the storage or memory keywords. Call data behaves almost like memory. It is an unmodifiable and temporary area that can be used to store function arguments. For example, in the preceding structs example, if we want to use only memory temporarily, we can do that by using the memory keyword when using the structure and assigning values to fields in the struct, as shown here. As copying between memory and storage can be quite expensive, specifying a location can be helpful to control the gas expenditure at times. Parameters of external functions use call data memory. By default, parameters of functions are stored in memory, whereas all other local variables make use of storage. State variables, on the other hand, are required to use storage. Mappings. Mappings are used for a key-to-value mapping. This is a way to associate a value with a key. All values in this map are already initialized with all zeros, as in the following, for example. This example shows that offers is declared as a mapping. Another example makes this clearer. This is basically a dictionary or a hash table where string values are mapped to integer values. The mapping named bids has the string packed mapped to value 10. Control structures. The control structures available in the Solidity language are if, else, do, while, for, break, continue, and return. They work exactly the same as other languages, such as the C language or JavaScript. Some examples are shown here. If x is equal to 0, then assign value 0 to y, else assign 1 to z. Do increment x while z is greater than 1, while increment z while x is greater than 0. For break and continue, perform some work until x is less than or equal to 10. This for loop will run 10 times. If z is 5, then break the for loop. It will continue the work in a similar vein, but when the condition is met, the loop will start again. Return is used to stop the execution of a function and returns an optional value. For example, it will stop the execution and return a value of 0. Events. Events in Solidity can be used to log certain events in EVM logs. These are quite useful when external interfaces are required to be notified of any change or event in the contract. These logs are stored on the blockchain in transaction logs. Logs cannot be accessed from the contracts but are used as a mechanism to notify change of state or the occurrence of an event, meeting a condition in the contract. In a simple example here, the value event will return true if the x parameter passed to the function matcher is equal to or greater than 10. Inheritance. Inheritance is supported in Solidity. The is keyword is used to derive a contract from another contract. In the following example, value checker 2 is derived from the value checker contract. The derived contract has access to all non-private members of the parent contract. In the preceding example, if the uint8 price equals 20 is changed to uint8 private price equals 20, then it will not be accessible by the value checker 2 contract. This is because now the member is declared as private, and thus it is not allowed to be accessed by any other contract. The error message that you will see when attempting to compile this contract is as follows. Libraries. Libraries are deployed only once at a specific address, and their code is called via the call code or delegate call opcode on the EVM. The key idea behind libraries is code reusability. They are similar to contracts and act as base contracts to the calling contracts. A library can be declared as shown in the following example. This library can then be called in the contract as shown here. First, it needs to be imported, and then it can be used anywhere in the code. A simple example is shown as follows. There are a few limitations with libraries. For example, they cannot have state variables and cannot inherit or be inherited. Moreover, they cannot receive ether either. This is in contrast to contracts, which can receive ether. Functions. Functions are pieces of code within a smart contract. For example, look at the following code block. In the preceding code example with contract test 1, we have defined a function called addition1 parentheses, which returns an unsigned integer after adding 2 to the value supplied via the variable x. initialized just before the function. In this case, 2 is supplied via variable x, and the function will return 4 by adding 2 to the value of x. It is a simple function, but demonstrates how functions work and what their different elements are. There are 2 function types, internal and external functions. Internal functions can be used only within the context of the current contract. External functions can be called via external function calls. A function in solidity can be marked as a constant. Constant functions cannot change anything in the contract. They only return values when they are invoked and do not cost any gas. This is the practical implementation of the concept of call, as discussed in the previous chapter. The syntax to declare a function is shown as follows. For example, here function is the keyword used to declare the function, addition is the name of the function, public is the visibility modifier, view is the state mutability modifier, returns is the keyword to specify what is returned from the function, and uint is the return type with the variable name y. Functions in Solidity are modules of code that are associated with a contract. Functions are declared with a name, optional parameters, access modifiers, state mutability modifiers, and an optional return type. This is shown in the following example. In the preceding code, function is the keyword used to declare the function. Order matcher is the function name, uint x is an optional parameter, private is the access modifier or specifier that controls access to the function from external contracts. View is an optional keyword used to specify that this function does not change anything in the contract, but is used only to retrieve values from the contract, and returns bool return value, is the optional return type of the function. After this introduction to functions in Solidity, let's consider some of their key elements, parameters, and modifiers. How to define a function. The syntax of defining a function is shown as follows. Function signature. Functions in Solidity are identified by their signature, which is the first 4 bytes of the CACAC 256 hash of its full signature string. This is also visible in the Remix IDE, as shown in the following screenshot. F9D55E21 is the first 4 bytes of the 32-byte CACAC 256 hash of the function named matcher. In this example, matcher has the signature hash of D99C89CB. This information is useful in order to build interfaces. Input parameters of a function. Input parameters of a function are declared in the form of data type parameter name. This example clarifies the concept where uint x and uint y are input parameters of the check values function. Output parameters of a function. Output parameters of a function are declared in the form of data type parameter name. This example shows a simple function returning a uint value. A function can return multiple values as well as take multiple inputs. In the preceding example function, getValue only returns one value, but a function can return up to 14 values of different data types. The names of the unused return parameters can optionally be omitted. An example of such a function could be, here when the code runs it will take 2 parameters as input x and y, add both and then assign them to z and a, and finally return z and a. For example, if we provide 1 and 1 for x and y respectively, then when the variables z and a are returned by the function, both will contain 2 as the result. Internal function calls. Functions within the context of the current contract can be called internally in a direct manner. These calls are made to call the functions that exist within the same contract. These calls result in simple jump calls at the EVM bytecode level. External function calls. External function calls are made via message calls from a contract to another contract. In this case, all function parameters are copied to the memory. If a call to an internal function is made using the this keyword, it is also considered an external call. The this variable is a pointer that refers to the current contract. It is explicitly convertible to an address, and all members of a contract are inherited from the address. Fallback functions. This is an unnamed function in a contract with no arguments and return data. This function executes every time Ether is received. It is required to be implemented within a contract if the contract is intended to receive Ether. Otherwise, an exception will be thrown and Ether will be returned. This function also executes if no other function signatures match in the contract. If the contract is expected to receive Ether, then the fallback function should be declared with the payable modifier. The payable is required, otherwise this function will not be able to receive any Ether. This function can be called using the address.call parentheses method, for example in the following. In this case, if the fallback function is called according to the conditions described earlier, it will call throw, which will roll back the state to what it was before making the call. It can also be some other construct than throw. For example, it can log an event that can be used as an alert to feed back the outcome of the call to the calling application. Modifier functions. These functions are used to change the behavior of a function and can be called before other functions. Usually they are used to check some conditions or verification before executing the function. Underscore, which is used in the modifier functions that will be replaced with the actual body of the function when the modifier is called. Basically, it symbolizes the function that needs to be guarded. This concept is similar to guard functions in other languages. Constructor function. This is an optional function that has the same name as the contract and is executed once a contract is created. Constructor functions cannot be called later on by users, and there is only one constructor allowed in a contract. This implies that no overloading functionality is available. Function visibility specifiers, access modifiers, access levels. Functions can be defined with 4 access specifiers as follows. External. These functions are accessible from other contracts and transactions. They cannot be called internally unless the this keyword is used. Public. By default, functions are public. They can be called either internally or by using messages. Internal. Internal functions are visible to other derived contracts from the parent contract. Private. Private functions are only visible to the same contract they are declared in. Function modifiers. Pure. This modifier prohibits access or modification to state. View. This modifier disables any modification to state. Payable. This modifier allows payment of Ether with a call. Constant. This modifier disallows access or modification to state. This is available before version 0.5.0 of Solidity. Now we've considered some of the defining features of functions. Let's consider how Solidity approaches handling errors. Error handling. Solidity provides various functions for error handling. By default in Solidity, whenever an error occurs, the state does not change and reverts back to the original state. Some constructs and convenience functions that are available for error handling in Solidity are introduced as follows. Assert. This is used to check for conditions and throw an exception if the condition is not met. Assert is intended to be used for internal errors and invariant checking. When called, this method results in an invalid opcode and any changes in the state are reverted back. Require. Similar to assert, this is used for checking conditions and throws an exception if the condition is not met. The difference is that require is used for validating inputs, return values or calls to external contracts. The method also results in reverting back to the original state. It can also take an optional parameter to provide a custom error message. Revert. This method aborts the execution and reverts the current call. It can also optionally take a parameter to return a custom error message to the caller. Try catch. This construct is used to handle a failure in an external call. Throw. Throw is used to stop execution. As a result, all state changes are reverted. In this case, no gas is returned to the transaction originator because all the remaining gas is consumed. This completes a brief introduction to the Solidity language. The language is very rich and under constant improvement. Detailed documentation and coding guidelines are available online at solidity.readthedocs.io/en/latest. Summary. This chapter started with the introduction of development tools for Ethereum, such as Ganache CLI. The installation of Node.js was also introduced, as most of the tools are JavaScript and Node.js based. Then we discussed some frameworks such as Truffle, along with local blockchain solutions for development and testing, such as Ganache and Drizzle. We also introduced Solidity in this chapter and explored different concepts such as value types, reference types, functions, and error handling concepts. We also learned how to write contracts using Solidity. In the next chapter, we will explore the topic of Web3, a JavaScript API that is used to communicate with the Ethereum blockchain.
Chapter 15. Introducing Web3. Web3 is a JavaScript library that can be used to communicate with an Ethereum node via RPC communication. Web3 works by exposing methods that have been enabled over RPC. This allows the development of user interfaces, UIs, that make use of the Web3 library in order to interact with contracts deployed over the blockchain. In this chapter, we'll explore the Web3 API and introduce some detailed examples of how smart contracts are written, tested, and deployed to the Ethereum blockchain. We will use various tools such as the Remix IDE and Ganache to develop and test smart contracts and look at the methods used to deploy smart contracts to Ethereum test networks and private networks. The chapter will explore how HTML and JavaScript front-ends can be developed to interact with smart contracts deployed on the blockchain, and introduce advanced libraries such as Drizzle. The topics we will cover are as follows: exploring Web3 with Geth, contract deployment, interacting with contracts via front-ends, development frameworks. We will start with Web3 and gradually build our knowledge with various tools and techniques for smart contract development. You will be able to test your knowledge in the bonus content pages for this book, where we will develop a project using all the techniques that this chapter will cover. Exploring Web3 with Geth. In order to expose the required APIs via Geth, the following command can be used. Web3 is a powerful API and can be explored by attaching a Geth instance. Later in this section, you will be introduced to the concepts and techniques of making use of Web3 via JavaScript, HTML, frontends. The Geth instance can be attached using the following command: $Geth attach ~etherprivate/geth.ipc. Once the Geth JavaScript console is running, Web3 can be queried. Now that we've introduced Web3, let's consider how the Remix IDE can be used to deploy a contract, and how the Geth console can interact with the deployed contract. Contract deployment. A simple contract can be deployed using Geth and interacted with using Web3 via the command line interface, CLI, that Geth provides, console or attach. The following are the steps to achieve that. As an example, the following source code will be used. Run the Geth client using the following command. Or alternatively, the following command can be run. We've used all these commands in different contexts before, and you can use any of them to run Geth. The difference is that the first command allows connectivity with the Remix IDE as we have specified. --rpc-cors domain https://remix.ethereum.org. If you need to use the Remix IDE, then use the first command. The second command allows localhost :7777 to access the RPC server exposed by Geth. This option is useful if you have an application running on this interface and you want to give it access to RPC. It also exposes RPC on port 8001 via the flag --RPC port 8001, which is useful in case you have some other service or application listening already on port 8545, which would mean that Geth won't be able to use that already in use port. This is because Geth listens on port 8545 for the HTTP RPC server by default. Alternatively, you can simply run the last command, which allows all incoming connections as --RPC ORS domain is set to *. If the Geth console is not already running, open another terminal and run the following command: $geth attach ~etherprivate/geth.ipc. In order to deploy a smart contract, we use the Web3 deployment script. The main elements of the script, the application binary interface, ABI, and the bytecode can be generated from the Remix IDE. To learn how to download and use the Remix IDE, refer to Chapter 13, Ethereum Development Environment. First, paste the following source code, as mentioned at the beginning of the section in the Remix IDE. We will discuss the Remix IDE in more detail later in this chapter. For now, we are using the IDE only to get the required elements, ABI and bytecode, for the Web3 deployment script used for deployment of the contract. Once the code is pasted in the Remix IDE, it will appear as follows in the Solidity compiler. Now create the Web3 deployment script as shown as follows. First, generate the ABI and bytecode by using the ABI and bytecode buttons in the Remix IDE, shown at the lower left side in Figure 15.2, and paste them in the following script after the web3.eth.contract and data:elements, respectively. Ensure that the accounts are unlocked. First, list the accounts by using the following command, which outputs account 0, first account, as shown here. Now unlock the account using the following command. It will need the passphrase, password, that you used originally when creating this account. Enter the password to unlock the account. For more convenience, the account can be unlocked permanently for the length of the Geth console/attach session by using the command shown here. Now we can open the Geth console that has been opened previously and deploy the contract. However, before deploying the contract, make sure that mining is running on the Geth node. The following command can be used to start mining under the Geth console. >miner.start parentheses. Now paste the previously mentioned Web3 deployment script in the Geth console as shown in the following screenshot. The previous screenshot shows the output as it looks when the Web3 deployment script is pasted in the Geth console for deployment. Note the data code section, which contains the bytecode of the smart contract. ABI and code can also be obtained by using the Solidity compiler, as shown in the following code snippets. In order to generate the ABI, we can use the command shown as follows. $solc-ABI valuechecker.sol. This command will produce the following output with the contract ABI in JSON format. The next step is to generate code, which we can use the following command to do. $solc-bin valuechecker.sol. This command will produce the binary represented as hex of the smart contract code. We can also see the relevant message in the Geth logs to verify that the contract creation transaction has been submitted. You will see messages similar to the one shown as follows. Also notice that in the Geth console, the following message appears as soon as the transaction is mined, indicating that the contract has been successfully mined. Notice that in the preceding output the transaction hash. After the contract is deployed successfully, you can query various attributes related to this contract, which we will also use later in this example, such as the contract address and ABI definition, as shown in the following screenshot. Remember, all of these commands are issued via the Geth console, which we have already opened and used for contract deployment. In order to make interaction with the contract easier, the address of the account can be assigned to a variable. There are a number of methods that are now exposed, and the contract can be further queried now, for example. We can now call the actual methods in the contract. A list of the various methods that have been exposed now can be seen as follows. The contract can be further queried as follows. First, we find the transaction hash, which identifies the transaction. Greater than valueChecker.transaction hash. The output of this command is the transaction hash of the contract creation transaction. We can also query the ABI using the following command. The output will be shown as follows. Note that it shows all the inputs and outputs of our example contract. In the following example, the matcher function is called with the arguments. Arguments, also called parameters, are the values passed to the functions. Remember that in the smart contract code shown in figure 15.2, there is a condition that checks if the value is equal to or greater than 10, and if so, the function returns true, otherwise it returns false. To test this, type the following commands into the Geth console that you have open. Pass 12 as an argument, which will return true as it is greater than 10. Pass 10 as an argument, which will return true as it is equal to 10. Pass 9 as an argument, which will return false as it is less than 10. In this section, we learned how to use the Remix IDE to create and deploy contracts. We also learned how the Geth console can be used to interact with a smart contract and explored which methods are available to interact with smart contracts on the blockchain. Now we'll see how we can interact with Geth using JSON RPC over HTTP. Post requests. It is possible to interact with Geth via JSON RPC over HTTP. For this purpose, the curl tool can be used. Curl is available at curl.haxx.se. An example is shown here to familiarize you with the post request and show how to make post request using curl. Before using the JSON RPC interface over HTTP, the Geth client should be started up with appropriate switches, as shown here. This switch will enable the Web3 interface over HTTP. The Linux command curl can be used for the purpose of communicating over HTTP, as shown in the following example. Retrieving the list of accounts. For example, in order to retrieve the list of accounts using the personal_list_accounts method, the following command can be used. This will return the output, a JSON object with the list of accounts. In the preceding curl command, --request is used to specify the request command. Post is the request, and --data is used to specify the parameters and values. Finally, localhost :8545 is used where the HTTP endpoint from Geth is opened. In this section, we covered how we can interact with the smart contract using the JSON RPC over HTTP. While this is a common way of interacting with the contracts, the examples we have seen so far are command line based. In the next section, we'll see how we can interact with the contracts by creating a user-friendly web interface. Interacting with contracts via frontends. It is desirable to interact with the contracts in a user-friendly manner via a web page. It is possible to interact with the contracts using the web3.js library from HTML, JS, CSS-based web pages. The HTML and JavaScript front end. The HTML content can be served using any HTTP web server, whereas web3.js can connect via local RPC to the running Ethereum client, Geth, and provide an interface to the contracts on the blockchain. This architecture can be visualized in the following diagram. If web3.js is not JavaScript front-end already installed, use these steps, otherwise move on to the next section, interacting with contracts via a web front-end. Installing web3.js JavaScript library. Web3, which we discussed earlier in this chapter, was looked at in the context of the Web3 API exposed by Geth. In this section, we will introduce the Web3 JavaScript library, web3.js, which is used to introduce different functionalities related to the Ethereum ecosystem in dApps. The web3.js library is a collection of several modules, which are listed as follows with the functionality that they provide. Web3-ETH, Ethereum blockchain and smart contracts. Web3-SHH, Whisper protocol, P2P communication and broadcast. Web3-BZZ, Swarm protocol, which provides decentralized storage. Web3-UTILS, provides helper functions for the app development. The web3.js library can be installed via npm by simply issuing the following command: $npm install web3. Web3.min.js, downloaded via npm, can be referenced in the HTML files. This can be found under node_modules. For example, the file can optionally be copied into the directory where the main application is and can be used from there. Once the file is successfully referenced in HTML or JavaScript, Web3 needs to be initialized by providing an HTTP provider. This is usually the link to the localhost HTTP endpoint, exposed by running the Geth client. This can be achieved using the following code. Once the provider is set, further interaction with the contracts and blockchain can be done using the Web3 object and its available methods. The Web3 object can be created using the following code. In this section, we have explored how to install web3.js, the Ethereum JavaScript API library, and how to create a Web3 object that can be used to interact with the smart contracts using the HTTP provider running on the local host as part of the Geth instance. Interacting with contracts via a web frontend. In the following section, an example will be presented that will make use of web3.js to allow interaction with the contracts via a web page served over a simple HTTP web server. So far, we have seen how we can interact with the contract using the Geth console via the command line. But in order for an application to be usable by end users, who will mostly be familiar with web interfaces, it becomes necessary to build web front-ends so that users can communicate with the back-end smart contracts using familiar web page interfaces. Creating an app.js JavaScript file. This can be achieved by following these steps. First, create a directory named /simplecontract/app, the home directory. This is the main directory under your user ID on Linux or Mac OS. This can be any directory, but in this example, the home directory is used. Then create a file named app.js and write or copy the following code into it. This file contains various elements. First, we created the Web3 object and provided a localhost Geth instance listening on port 8545 as the Web3 provider. After this, the web3.eth.accounts is selected as the account with which all the interactions will be performed with the smart contract. Next, the API is provided, which serves as the interface between the user and the contract. It can be queried using Geth, generated using the Solidity compiler, or copied directly from the Remix IDE contract details. After this, the simple contract is created, which refers to the smart contract with address 0x82012, B760, 1FD 23669B, 50BB 7DD, 794, 609, 70, CE 386E3, Finally, we declared three functions: call matcher true, parentheses, call matcher false, parentheses, and my function, parentheses, which we will explain further shortly. First, we create the front-end web page. For this, we create a file named index.html with the source code shown as follows. This file will serve as the front end of our decentralized application. In other words, it provides the UI for interacting with the smart contracts. First, we refer to the JavaScript web3.js library and app.js, which we created earlier in this section. This will allow the HTML file to call required functions from these files. After that, standard HTML is used to create an input text field so that users can enter the values. Then we use the onClick event to call the myFunction parentheses function that we declared in our JavaScript app.js file. Finally, two onClick events with buttons called true and call false are used to call the call matcher true parentheses and call matcher false parentheses functions respectively. We are keeping this very simple on purpose. There is no direct need to use jQuery, React, or Angular here, which would be a separate topic. Nevertheless, these front-end frameworks make development easier and a lot faster, and are commonly used for blockchain-related JavaScript front-end development. In order to keep things simple, we are not going to use any front-end JavaScript frameworks in this section, as the main aim is to focus on blockchain technology and not the HTML, CSS, or JavaScript UI frameworks. However, in the bonus source pack for this chapter, we will see an example of creating UIs using React with Drizzle. In this part of the example, we have created a web frontend and a JavaScript file backend where we have defined all the functions required for our application. The app.js file we created in this section is the main JavaScript file that contains the code to create a Web3 object. It also provides methods that are used to interact with the contract on the blockchain. An explanation of the code previously used is given in the next sections. Creating a Web3 object. The first step when creating a Web3.js-based application is to create the Web3 object. It is created by selecting the appropriate available Web3 provider, which serves as an entry point to the blockchain through the HTTP RPC server exposed on a locally running Geth node. This code checks whether there is already an available Web3 provider. If yes, then it will set the provider to the current provider. Otherwise, it sets the provider to localhost 8545. This is where the local instance of Geth is exposing the HTTP RPC server. In other words, the Geth instance is running an HTTP RPC server, which is listening on port 8545. Checking availability by calling the Web3 method. This line of code simply uses console.log to print the simple contract attributes in order to verify the successful creation of the contract. Once this call is executed, it will display various contract attributes indicating that the Web3 object has been created successfully and HTTP provider is available. Any other call can be used to verify the availability, but here printing simple contract attributes has been used. In this part of the example, we have created a simple contract instance and then used console.log to display some attributes of the contract, which indicates the successful creation of the simple contract instance. In the next stage of this example, we will explore how the contract functions can be called. Calling contract functions. Once the Web3 object is correctly created and a simple contract instance is created, in the previous section, calls to the contract functions can be made easily as shown in the following code. The preceding code shows three simple functions: call matcher true parentheses, call matcher false parentheses, and myFunction parentheses. Call matcher true parentheses simply calls the smart contract function matcher using the simple contract object we created in the app.js file we created earlier. Similarly, call matcher false parentheses calls the smart contracts matcher function by providing a value of 1. Finally, the my function parentheses function is defined, which contains simple logic to read the value provided by the user on the web page in the txt value text box, and uses that value to call the smart contracts matcher function. After that, the return value is also logged in the debug console, available in browsers by using console.log. Calls can be made using simple contract instance.matcher.call, and then by passing the value for the argument. Recall the matcher function in the Solidity code. Function matcher open parentheses uint8x close parentheses returns open parentheses bool close parentheses. It takes one argument x of type uint8 and returns a Boolean value either true or false. Accordingly, the call is made to the contract as shown here. var txn equals simple contract instance.matcher.call open parentheses 12 close parentheses semicolon. In the preceding example, console.log is used to print the value returned by the function call. Once the result of the call is available in the txn variable, it can be used anywhere throughout the program, for example as a parameter for another JavaScript function. Finally, the HTML file named index.html is created with the following code. This HTML file will serve as the front-end UI for the users, who can browse to this page served via an HTTP server to interact with the smart contract. It is recommended that a web server is running in order to serve the HTML content, index.html as an example. Alternatively, the file can be browsed from the file system, but that can cause some issues related to serving the content correctly with larger projects. As a good practice, always use a web server. A web server in Python can be started using the following command. This server will serve the HTML content from the same directory that it has been run from. $python-m simple HTTP server 7777. Now, any browser can be used to view the web page served over a TC port 7777. This is shown in the following screenshot. As the values are hard-coded in the code for simplicity, two buttons shown in the screenshot, call true and call false, have been created in index.html. Both of these buttons call functions with hard-coded values. This is just to demonstrate that parameters are being passed to the contract via Web3 and values are being returned accordingly. There are three functions being called behind these buttons. We will describe them as follows. 1. The getDecision button returns the decision from the contract. The getDecision button invokes the smart contracts matcher function with the value entered on the web page. The variable x contains the value passed to this function via the web page, which is 12. As the value is 12, which is greater than 10, the getDecision button will return true. 2. The callTrue button will call the matcher function with a value that is always greater than 10, such as 12, returning always true. The callMatcherTrue parentheses method has a hard-coded value of 12, which is sent to the contract using the following code. Simple contract instance.matcher.call open parentheses 12 close parentheses. The return value is printed in the console using the following code, which first invokes the matcher function and then assigns the value to the txn variable to be printed later in the console. 3. The callFalse button invokes the callMatcherFalse parentheses function. The callMatcherFalse parentheses function works by passing a hard-coded value of 1 to the contract using this code. Simple contract instance.matcher.call parentheses 1 close parentheses. The return value is printed accordingly. This example demonstrates how the Web3 library can be used to interact with the contracts on the Ethereum blockchain. First, we created a web frontend using the JavaScript app.js file and the HTML file. We also included the Web3 library in our HTML so that we could create the Web3 object and use that to interact with the deployed smart contract. In the next section, we'll explore some development frameworks that aid Ethereum development, including a commonly used framework called Truffle. Development frameworks. There are various development frameworks now available for Ethereum, as seen in the examples discussed earlier. It can be quite time-consuming to deploy the contracts via manual means. This is where Truffle and similar frameworks such as Embark can be used to make the process simpler and quicker. We have chosen Truffle because it has a more active developer community and is currently the most widely used framework for Ethereum development. However, note that there is no best framework, as all frameworks aim to provide methods to make development, testing, and deployment easier. In the next section, you will be introduced to an example project to demonstrate the usage of the Truffle framework. Using Truffle to develop a decentralized application. We discussed Truffle briefly in Chapter 14, Development Tools and Frameworks. In this section, we will see an example project that will demonstrate how Truffle can be used to develop a decentralized application. We will see all the steps involved in this process, such as initialization, testing, migration, and deployment. First, we will see the installation process. Installing and initializing Truffle. If Truffle is not already installed, it can be installed by running the following command: $npm install-g Truffle. Next, Truffle can be initialized by running the following commands. First, create a directory for the project. For example, $mkdir test_the_app. Then, change the directory to the newly created test_the_app and run the following command, $truffle init. Once the command is successful, it will create the directory structure as shown here. This can be viewed using the tree command in Linux. This command creates 3 main directories named Contracts, Migrations, and Test. As seen in the preceding example, a total of 3 directories and 4 files have been created. The directories are defined here. Contracts. This directory contains Solidity contract source code files. This is where Truffle will look for Solidity contract files during migration. Migration. This directory has all the deployment scripts. Test. As the name suggests, this directory contains relevant test files for application and contracts. Finally, Truffle configuration is stored in the truffle.js file, which is created in the root folder of the project from where Truffle init was run. When Truffle init is run, it will create a skeleton tree with files and directories. In previous versions of Truffle, this used to produce a project named Metacoin, but now this project is now available as a Truffle box. Now that we have initialized Truffle, let's see how it is used to compile, test, and migrate smart contracts. Compiling, testing, and migrating using Truffle. In this section, we will demonstrate how to use various operations available in Truffle. We will introduce how to use compilation, testing, and migration commands in Truffle to deploy and test Truffle boxes, which are essentially sample projects available with Truffle. We will use the Metacoin Truffle box. Later, further examples will be shown on how to use Truffle for custom projects. We will use Ganache as a local blockchain to provide the RPC interface. Make sure that Ganache is running in the background and mining. In the following example, Ganache is running on port 7545 with 10 accounts. These options can be changed in the Settings option in Ganache as shown in the following screenshot. We will use the Ganache workspace that we saved in Chapter 14, Development Tools and Frameworks. Alternatively, a new environment can also be set up. After the successful setup of Ganache, the following steps need to be performed in order to unpack the Webpack truffle box and run the Metacoin project. This example provides a solid foundation for the upcoming sections. With this exercise, we will learn how a sample project available with Truffle can be downloaded, and how we perform compilation, testing, and migration of the contracts available with this sample onto Ganache. 1. First, create a new directory. 2. Now unbox the Webpack sample from Truffle. 3. Edit the truffle.js file. If Ganache is running on a different port, then change the port from the default to where Ganache is listening. Note the settings provided in the screenshot in Figure 15.8. Edit the file and uncomment the defaults. The file should look like the one shown here. Now, after unboxing the Webpack sample and making the necessary configuration changes, we are ready to compile all the contracts. 4. Now run the following command to compile all the contracts. This will show the following output. 5. Now we can test using the truffle test command as shown here. This command will produce the output shown as follows, indicating the progress of the testing process. We can also see that in Ganache, the transactions are being processed as a result of running the test. 6. Once testing is completed, we can migrate to the blockchain using the following command. Migration will use the settings available in truffle.js that we edited in the second step of this process to point to the port where Ganache is running. This is achieved by issuing the following command, $truffle migrate. The output is shown as follows. Notice that when migration runs, it will reflect on Ganache. For example, the balance of accounts will go down, and you can also view transactions that have been executed. Also notice that the account shown in the screenshot corresponds with what is shown in Ganache. Notice that the migration we have just performed is reflected in Ganache with the accounts shown previously. You can see balance updating in Ganache as the transactions run and ETH is consumed. In the Ganache workspace, we can also add the Truffle project to enable extra features. For this, click on the upper right-hand corner gear icon and open the settings screen. Add the Truffle project as shown here. Save and restart to commit the changes. When Ganache is back up again, you will be able to see additional information about the contract as shown in the following screenshot. In this section so far, we've explored how Truffle can be used to compile, test, and deploy smart contracts on the blockchain. We use Ganache, the Ethereum personal blockchain, a simulated version of the Ethereum blockchain, to perform all the exercises. Now we can interact with the contract using the Truffle console. We will explore this in the following section. Interacting with the contract. Truffle also provides a console, a CLI, that allows interaction with the contracts. All deployed contracts are already instantiated and ready to use in the console. This is an REPL-based interface, meaning read, evaluate, and print loop. Similarly, in the Get client via attach or console, REPL is used via exposing the JavaScript runtime environment. JSRE. 1. The console can be accessed by issuing the following command, $truffle console. 2. This will open a CLI. Once the console is available, various methods can be run in order to query the contract. A list of methods can be displayed by typing the preceding command and tab completing. 3. Other methods can also be called in order to interact with the contract. For example, in order to retrieve the address of the contract, the following method can be called using the Truffle console. Truffle development greater than metacoin.address. This address is also shown in contract creation transaction in Ganache. A few examples of other methods that we can call in the Truffle console are shown here. 4. To query the accounts available, enter the following command. Truffle development greater than metacoin.web3.eth.getAccounts parentheses. This will return the output shown here. 5. To query the balance of the contract, enter the following command. This will show the output shown here. This is the first account shown in Ganache in the preceding screenshot. 0x2366898488003CB00CB8 2E 6E 6DE 3F 6D17C 4AA 9ADA, and the output returned a string with the value 99945700780000000. 6. To end a session with the Truffle console, the .exit command is used. This completes our introduction to the sample Webpack Trufflebox and the Metacoin application using Truffle. In this section, we discovered how Truffle can be used to interact with the deployed smart contracts. Metacoin in this section is an example of a decentralized application. However, we use this merely as an example to learn how Truffle works. In this chapter's bonus content pages, we will use the techniques that we learned in this section to develop our own decentralized application. In the next section, we will see how a contract can be developed from scratch, tested, and deployed using Truffle, Ganache, and our private net. Using Truffle to test and deploy smart contracts. This section will demonstrate how we can use Truffle for testing and deploying smart contracts. Let's look at an example of a simple contract in Solidity, which performs addition. We will see how migrations and tests can be created for this contract with the following steps. 1. Create a directory named simple, $mkdir simple. 2. Change directory to simple, $cd simple. 3. Initialize Truffle to create a skeleton structure for smart contract development, $truffle init. The tree structure produced by the init command is as follows. 4. Place the two files, addition.sol and migrations.sol, in the contracts directory. The code for both of these files is listed as follows. 5. Now compile the contracts. $truffle compile. 6. Under the migration folder, place two files, 1_initial_migration.js and 2_deploy_contracts.js as shown here. 7. Under the test folder, place the file testaddition.sol. This will be used for unit testing. 8. The test is run using the command shown here, $truffle test. 9. This means that our tests are successful. Once the tests are successful, we can deploy it to the network, in our case, Ganache. $truffle migrate. In Ganache, we see this activity, which corresponds to our migration activity. As the addition contract is already instantiated and available in the Truffle console, it becomes quite easy to interact with the contract. In order to interact with the contract, the following methods can be used. 1. Run the following command, $truffle console. This will open the Truffle console, which will allow interaction with the contract. For example, in order to retrieve the address of the deployed contract, the following method can be called. Truffle open parentheses development close parentheses greater than addition.address. 2. To call the functions from within the contract, the deployed method is used with the contract functions. An example is shown here. First, instantiate the contract. 3. Now call the addx function. Truffle open parentheses development close parentheses greater than addition contract.addx open parentheses 2,2 close parentheses. This will produce the following output indicating the execution status of the transaction that was created as a result of calling the addx function. We see the transaction in Ganache too. 4. Finally, we can call the retrieveX function to see the current value after addition. Truffle open parentheses development close parentheses greater than additionContract.retrieveX parentheses. Finally, we see the value 4 returned by the contract. In this section, we created a simple smart contract that performs an addition function and learn how the Truffle framework can be used to test and deploy the smart contract. We also learned how to interact with the smart contract using the Truffle console. In the next section, we will look at IPFS, which can serve as the decentralized storage layer for a decentralized ecosystem. We will now see how we can host one of our apps on IPFS. Deployment on decentralized storage using IPFS. As discussed in Chapter 1, Blockchain 101, in order to fully benefit from decentralized platforms, it is desirable that you decentralize the storage and communication layer too, in addition to decentralized state computation, blockchain. Traditionally, web content is served via centralized servers, but that part can also be decentralized using distributed file systems. The HTML content shown in the earlier examples can be stored on a distributed and decentralized IPFS network in order to achieve enhanced decentralization. IPFS can be installed by following this process. 1. Download the IPFS package from https://dist.ipfs.io/#go-ipfs and decompress the .gz file. $tar xvfc go-ipfs_v0.4.23_darwin-amd64.tar. 2. Change directory to where the files have been decompressed. $cd go-ipfs. 3. Start the installation. $./install.sh. This will produce the following output. 4. Check the version to verify the installation. $IPFS version. This will produce the following output. 5. Initialize the IPFS node. $IPFS init. This will produce the following output. 6. Enter the following command to ensure that IPFS has been successfully installed. This will produce the following output. 7. Now start the IPFS daemon. $IPFS daemon. This will produce the following output. 8. Copy files onto IPFS using the following command. This will produce the following output, indicating the progress of adding the pages to IPFS. Now it can be accessed in the browser as follows. 9. Finally, in order to make the changes permanent, the following command can be used. This will show the following output. The preceding example demonstrated how IPFS can be used to provide decentralized storage for the web part UI of smart contracts. Remember that in Chapter 1, Blockchain 101, we described that a decentralized application consists of a front-end interface, usually a web interface, back-end smart contracts on a blockchain, and the underlying blockchain. We have covered all these elements in this example and created a decentralized application. To try your hand at a start-to-finish application deployment project, please go to this book's bonus online content pages here, static.pack-t-cdn.com/download/altcoins_ethereum_projects_and_more_bonus_content.pdf. You will build and deploy a proof of idea contract using Truffle before creating a UI frontend for it with a tool called Drizzle. Summary: this chapter started with the introduction of Web3. We explored various methods to develop smart contracts. Also, we saw how the contract can be tested and verified using local test blockchain before implementation on a public blockchain or private production blockchain. We worked with various tools such as Ganache, the Geth Client Console, and the Remix IDE to develop, test, and deploy smart contracts. Moreover, the Truffle framework was also used to test
and migrate smart contracts.
We also explored how IPFS can be used to host the web pages that we created for our DApp, serving as the decentralized storage layer of the blockchain ecosystem. In the bonus content for this chapter, which we strongly encourage you to use, we practice the techniques we learned in this chapter, plus other advanced topics such as Drizzle, to create the front ends for DApps easily. In the next chapter, we will introduce Serenity, Ethereum 2.0, which is the final version of Ethereum.
Chapter 16: Serenity. Ethereum 1.0 is the current version of Ethereum, with Berlin being the latest release, or update. The public Ethereum mainnet available today runs the Ethereum 1.0 protocol. Serenity is the name given to Ethereum version 2.0. The vision behind Ethereum 2.0 is to ultimately transition into a more scalable, performant, and secure version of Ethereum that will serve as the world computer, which is Ethereum's original vision. The concept of a world computer was introduced with Ethereum 1.0, in which a global, decentralized network of interconnected nodes runs peer-to-peer contracts without the limitation of shutting down or being censored or hacked. This vision started with Ethereum 1.0 and gained a lot of traction. However, challenges such as scalability, privacy, and performance somewhat hindered mass adoption. Ethereum 2.0 is expected to address these issues in pursuit of becoming a world computer. In Chapter 11, Ethereum 101, we saw that Ethereum is being released in a number of phases, with the first version being called Frontier, and with Serenity being the projected final version. Currently, we are at a Metropolitan, with the latest hard fork upgrade of Ethereum being called Istanbul. All these upgrades are taking Ethereum closer to Ethereum 2.0, which is currently being built, with Phase 0 expected to be launched by late 2020. In this chapter, we will cover Serenity, the update that will introduce Ethereum version 2.0. We will explore the theoretical foundations and understand many concepts behind the need for and development of Ethereum 2.0. In the book's bonus content pages, which we strongly encourage readers to utilize, we will also explore how Ethereum 2.0 clients can be set up. The topics that we cover are listed as follows: Ethereum 2.0, an overview, development phases, architecture. Before we delve into the Ethereum 2.0 architecture and other technical details, it is important to understand the vision and motivation behind its development. We'll describe these in the next section. Ethereum 2.0, an overview. Based on the problem presented by Vitalik Buterin, an Ethereum co-founder in 2015, it is understood that only two of the three main core properties of a blockchain can be utilized at a time. These three core properties are the following: decentralization, scalability, security, or consistency. This is known as the scalability trilemma, and is seen as a fundamental problem that needs to be addressed before global adoption of the Ethereum blockchain. This concept is visualized in the following diagram. Intensive research is underway with Phase 0 already near release. The aim is to address this trilemma and find the right balance between all three properties, instead of compromising and only choosing two of the three. With the release of Proof of Stake, POS, sharding, and EWASM, a balanced combination of all these three properties, that is, decentralization, scalability, and security, consistency, can be achieved. Having now discussed the high-level problem facing Ethereum, we can go on to look at some fundamental elements of Ethereum 2.0, starting with some specific goals. Goals. The major goals behind the development of Serenity can be divided into the following different dimensions. Reduce complexity. One of the main aims of Ethereum 2.0 is simplicity, even if there are some trade-offs with efficiency. Resiliency. The goal of resiliency ensures that the liveness of the network can be maintained even in the event of major network partitions. Increased security. With the advent of quantum cryptography and in order to mitigate the threats faced by cryptography in the post-quantum world, it is envisaged that in Ethereum 2.0, quantum-resistant cryptography, or at least easy pluggability of quantum-resistant elements, will be introduced, so that the blockchain remains secure even in a post-quantum world. Increased participation. It is also expected that greater participation of validators will help with improved security and overall participation. Increased performance. Instead of requiring specialist hardware or high-end CPUs and GPUs for performing validation activities in Ethereum 2.0, it is expected that validation activities will be performed by using typical consumer computers with the usual resources. With the introduction of POS, faster block time is expected. This also results in increased performance. Now that we have covered the main goals of Ethereum 2.0, we can dive into its more specific features. Main features. The main features of Serenity include a switch from a proof-of-work POW-based chain to a POS-based chain, which will make the network more decentralized, efficient, and faster. Secondly, EWASM, an improved version of the Ethereum Virtual Machine (EVM), is envisaged, which will make code execution faster, hence resulting in an overall performance gain. Another feature is sharding, which introduces the concept of shard chains and allows increased transaction throughput and immediate finality. Finally, sidechains will be used to enhance privacy, permissions, and governance. We touched briefly earlier on the roadmap of Ethereum, and next we describe the roadmap in detail so that readers can understand the past, present, and future of Ethereum. Roadmap of Ethereum. In this section, we look at the roadmap of Ethereum. The following list of Ethereum's main releases shows how Ethereum has evolved over time, along with its version of eventually achieving a world computer, a scalable, decentralized, and secure blockchain network. July 2015, Frontier. March 2016, Homestead. October 2017, Byzantium. February 2019, Constantinople. December 2019, Istanbul. Late 2020, Berlin. Late 2020, Beacon Chain, Serenity Phase 0. 2020, Shard Chains, Serenity Phase 1. 2021, Execution Environments, EWASM, Serenity Phase 2. 2022, Further Scalability and Improvements, Serenity Phase 3. As indicated here, the development of Ethereum 2.0 is divided into phases. In the next section, we will discuss the 4 major phases of Serenity development and what is involved in each phase. Development phases. The 4 phases in the development of Ethereum 2.0 are focused on various features of the blockchain. The main work included in Phase 0 is around the management of validators and the staking mechanism. In addition, this phase also includes block proposer selection, consensus mechanism rules, and a reward-penalty mechanism. Phase 1 includes the development of shard chains and blocks along with the cross-linking anchoring of shard blocks to the beacon chain, the core system chain. Phase 1.5, also known as the merge, is where Ethereum mainnet will transit into Ethereum 2, most likely by becoming a shard chain of Ethereum 2.0. The next stage, Phase 2, is focused on execution environment upgrades, and includes a VM upgrade to EWASM along with cross-shard communication and access to execution environments. Moreover, Phase 2 introduces the ability to run and interact with smart contracts. Currently, the specification is not final and might be subject to change. Phase 3 is envisaged to be a continuous improvement and maintenance stage where a complete Ethereum 2.0 chain will be running and evolving into a more mature and feature-rich blockchain. Now we will explain each phase and its features in detail. Phase 0. Phase 0 is the first phase of Ethereum 2.0 development. This stage involves the creation of a core system chain called the beacon chain, which can be considered the backbone of the entire Ethereum 2.0 chain system. After Phase 0 is complete, there will be two chains in existence: the original Ethereum 1.0 chain and a new chain called the beacon chain. These chains will operate in parallel. The Phase 0 specification and development can be further divided into multiple categories, the first of which is the beacon chain. The beacon chain. The beacon chain is the core system chain and manages the Casper POS consensus mechanism for itself and all of these shard chains. It is also used to store and maintain the registry of validators. Validators are nodes that participate in the POS consensus mechanism of Ethereum 2.0. The beacon chain has a number of features, listed as follows. Production of good quality randomness, which will be used for selecting block proposers and attestation committees without bias. Currently, a RANDAO-based scheme is prominent. However, other options such as BLS-based and Stark-based schemes have been considered in the past. RANDAO is a pseudo-random process that selects proposers for each slot in every epoch and rearranges the validators in the committees. Provision of attestation, which essentially means availability votes for a block in a shard chain. An adequate number of attestations for a shard block will result in the creation of a cross-link, which provides confirmation for shard blocks in the beacon chain. Validator and stake management. Provision of validator sets, committees, for voting on proposed blocks. Enforcement of the consensus mechanism and the reward and penalty mechanisms. Serving as a central system chain where shards can write their states so that cross-shard transactions can be enabled. In order to participate in the beacon chain, some beacon chain client or node software is required. We will discuss this next. Beacon nodes. The beacon node is the primary link in the beacon chain that forms the central core of the Ethereum 2.0 blockchain. The beacon node's responsibilities include synchronization of the beacon chain with other peers. It performs attestation of blocks and runs an RPC server to provide critical information to the validators regarding assignments and block attestation. In addition, it also handles state transition and acts as a source of randomness for the validator assignment process. The beacon node also serves as a listener for deposit events in the Ethereum 2.0 chain, as well as creating and managing validator sets. A beacon node synchronizes with the shards and it keeps a synchronized clock with other nodes on the beacon chain to ensure the application of penalty rules. Slashing. In a beacon node, various services based on the responsibilities mentioned previously are implemented. These include the blockchain service, synchronization service, operations service, Ethereum 2.0 service, public RPC server, and the P2P networking service. To participate in the beacon chain, a beacon chain client or node is required. Based on the Ethereum 2.0 specification, this client is being developed by a number of different teams. In the supplementary resources associated with this chapter, we will look at Prism. There are, however, many other teams that are developing Ethereum 2.0 clients in a variety of languages. A non-exhaustive list is presented as follows. By accessing this book's bonus content pages here, we will learn how the Ethereum 2.0 client from the Prismatic Labs can be installed and run. In addition, we will also perform some experiments to explore various features of Ethereum 2.0. In the next section, we introduce validator nodes, which serve as block proposers and attesters on the network as part of the POS mechanism in Ethereum 2.0. Validator nodes can be thought of in the same way as the miners in Ethereum 1.0, and are developed as per the specification finalized for Phase 0 of Ethereum 2.0. Validator nodes. A validator node, also referred to as a validator client, actively participates in the consensus mechanism to propose blocks and provide attestations. A user can stake a minimum of 32 Ethereum to get the ability to verify and attest to the validity of blocks. As validators participate in the consensus mechanism to secure the protocol, they are incentivized financially for their effort. The validators earn Ether, which is valid in Ethereum 2.0, Ethereum 2, as reward if their attestation is accepted. A validator has to perform a number of configurations before they can deposit Ether as a stake to become a validator. Once they are accepted, they become part of the validator registry that is stored and maintained on the Beacon chain. The first step for a node to become a validator is to generate a public-private key pair. For this purpose, the BLS 12-381 curve is used, which is a new zk-SNARK curve construction. A second private public key pair called the BLS withdrawal key is also required. These withdrawal credentials are used to withdraw funds. After this, the users have to deposit a minimum of 32 Ether, normal Ethereum 1.0 POW chain Ether, to a deposit contract. Once the deposit is made and processed, the validator is activated. At this point, it becomes part of the Beacon chain's set of validators. The key functions that a validator client performs are listed as follows. New block proposal, attestation provision for blocks proposed by other validators, attestation aggregation, connection with a trusted Beacon node to listen for new validator assignments and shuffling, shard chain synchronization with the Beacon chain. A validator is assigned a status based on its current state. It can have 6 statuses: deposited, pending, activated, slashed, exited, and withdrawable. Deposited status means that a validator has made a valid deposit and is registered in the Beacon chain state. Pending means that the validator is eligible for activation. Activated means that the activator is active. Slashed means the validator has lost a portion of their stake. Exited means the validator has exited from the validator set. And withdrawable indicates that the validator is able to withdraw funds. A withdrawable state occurs after a validator has exited and roughly 27 hours have passed. A validator can be in multiple states simultaneously. For example, a validator can be in both the active and slash states at the same time. Honest validator behavior is incentivized as part of the POS mechanism, and this honest behavior results in what is referred to as slashing. Slashing results in the removal of a validator from the validator committee, the active validator set, and a burning of a portion of its deposited funds. Slashing serves 2 purposes. First, it makes it prohibitively expensive to attack Ethereum 2.0, and secondly, it enforces the validators to actively perform their duties, functions. For example, a validator going offline when it is supposed to be actively participating in the consensus is penalized for its inactivity. There are 3 scenarios when slashing can occur. First is proposer slashing, which is when a validator signs 2 different blocks on the Beacon chain in the same epoch. The second case where slashing can occur is when a validator signs 2 conflicting attestations. Thirdly, slashing can also occur when a validator, when attesting, signs an attestation that surrounds another attestation. In other words, it means that this scenario occurs when a validator first attests to one version of the chain and then later attests another version of the chain, resulting in confusion as to which chain the validator actually supports. When any of the 3 preceding scenarios occur, the offending node is reported by a whistleblowing validator. The whistleblowing node creates a message containing evidence of the offense, sends it to a proposer to include it in a block, and propagates it on the network. In phase 0, the total slashing reward is taken by the proposer, and the whistleblowing validator does not get any reward.
This has the potential to change in Phase 1, where both actors might be rewarded. Also, remember that penalization and slashing are two related but different concepts. Penalization results in a decrease in the balance of a validator as a result of, for example, being inactive or going offline. On the other hand, slashing results in a forceful exit from the beacon chain, along with the responsible validator's deposit being penalized in every epoch for as long as it has to wait for its turn in the exit queue to leave the chain. Slashing and penalty calculations are based on several factors with various variables, such as the length of validator inactivity and the type of the offense that triggered the slashing. Moreover, a penalty is applied at various points in the slashing process. For example, a minimum penalty of effective balance of slashed validator /32 is applied when a validator proposer includes the message reporting the offense from the whistleblower in a block. After that, at the beginning of each epoch, a penalty calculated as 3 * base reward is applied. Another penalty is applied between the time of inclusion of the whistleblowing message in a block and the time when the slashed validator is able to withdraw. Earning rewards by staking Ether in the deposit contract also depends on several factors. A simple example is that if someone stakes 32 Ether with a current price of, for example, $240 per Ethereum, with validator uptime of 80%, the annual interest earned will be around 8%. The base reward is calculated as per the following formula from the Phase 0 specification. Here, base reward factor is set at the default value of 64, and the base rewards per epoch value is 4. The effective balance is used to calculate the proportion of rewards and penalties applied to a validator. It is based on the validator's balance and the previous effective balance. The maximum effective balance can always be only up to 32 Ethereum, even if the actual balance is 1000 Ethereum. The effective balance will still be 32 Ethereum. There are various calculators available online that can calculate the expected return of staking Ether from Ethereum 1.0 in the Ethereum 2.0 network. As these sections have demonstrated in Ethereum 2.0, Phase 0 there are 3 main components: the beacon chain, beacon nodes, and validator nodes. In the next section, we highlight some key differences between a beacon node and a validator node. Beacon and validator node comparison. The key differences between the beacon and validator nodes are listed in the following table. The architecture of Ethereum 2.0 is no longer a single node-based architecture like Ethereum, where there is only a single type of node that can perform all functions, such as mining and securing the chain. In Ethereum 2.0, there are 2 distinct types of nodes, beacon chain nodes and validator nodes. The key differences between these node types are presented in the following table. Being a POS-based blockchain, Ethereum 2.0 must have the ability to take deposits from users as a stake. This requirement in Phase 0 is addressed by a deposit contract. We will explain the features of a deposit contract next. Deposit contracts. Deposit contracts were created on the Ethereum 1.0 chain. This kind of smart contract is used for depositing ETH on the beacon chain. Currently, there is a test deposit contract written in Viper available on the Goerli testnet for curious readers, which can be accessed at the following address. An event is emitted every time a deposit is made. This event is composed of several fields as shown here. This log is consumed by the beacon chain. Another important feature of the Ethereum 2.0 beacon chain is a new rule for deciding which chain to choose in the case of a fork. We will discuss that next. Fork choice. The fork choice rule in Ethereum 2.0 is called Latest Message Driven Greediest Heaviest Observed Subtree, or LMD Ghost. Remember, we discussed the Greediest Heaviest Observed Subtree rule, Ghost, in the context of Ethereum mining in Chapter 11 Ethereum 101. LMD Ghost is a variant of Ghost that was implemented in Ethereum with some modifications.
LMD Ghost governs a fork handling mechanism to ensure that in the case of a fork, the correct and honest chain is automatically chosen. As a general rule, the honest chain is the one that has the most attestation and stake weight. In the event of a fork, the clients will use this fork choice rule to select the correct, honest chain. Forks may occur due to the actions of colluding participants. However, beacon chains' random selection of validators mitigates that to some extent, because validators do not know in advance when they will be selected. Another mechanism relevant to chain integrity is finality, which is the assurance that a block, once finalized, will not revert back. To achieve this, a mechanism called Casper, the Friendly Finality Gadget, Casper FFG, is implemented in Ethereum 2.0. In the next section, we introduce another important element that deals with all the networking requirements of Ethereum 2.0, the P2P interface. P2P interface networking. This element deals with the networking interfaces and protocols for the Ethereum 2.0 blockchain. There are three main dimensions addressed in the development of Ethereum P2P networking elements: the gossip domain, the discovery domain, the request-response domain. The networking specification also covers the essentials of a test network where multiple clients can run simultaneously, that is, the interoperability of the test network and mainnet launch. In order to achieve interoperability, all Ethereum 2.0 client implementations must support the TCP libp2p transport. This must also be enabled for both incoming and outgoing connections. Implementers may choose not to implement an IPv4 addressing scheme for the mainnet. Ethereum 2.0 may implement an inbound connectivity feature only for IPv6, but the clients must support both inbound and outbound connections for both IPv4 and IPv6 addresses. Some further products of Phase 0 development are introduced next. ETH2. ETH2 is the new digital currency for Ethereum 2.0, which is a new asset of validator nodes stakers in the consensus mechanism. It will be created as an incentive reward for validating the beacon chain and shards, and by purchasing it via the deposit contract using ETH1 currency, also called a registration contract. ETH1 is expected to transition into ETH2 completely, but ETH1 may still exist alongside ETH2. It is speculated that ETH1 may become a shard chain for the beacon chain, or ETH1 could be left alone and only new shard chains will be created. Also, due to the current vast ecosystem built around Ethereum 1.0 and the technical complexities of the transition to Ethereum 2.0, as a shard chain, it may result in some insuperable challenges, which could lead to Ethereum 1.0 being left as it is. Simple Serialize. Simple Serialize, or SSZ for short, is the algorithm standard for providing serialization abilities for all data structures in Ethereum 2.0 client software. SSZ has support for many data types such as Boolean, bool, unsigned integers, uint8, uint16, uint32, and uint64, slices, arrays, structs, and pointers. BLS cryptography. BLS cryptography, BLS 12-381, is used extensively in Ethereum 2.0 to provide security and efficient verification of digital signatures. BLS, short for Boni-Lind-Shacham signatures, allows the aggregation of cryptographic signatures to contribute to the scalability of the network. BLS is used by validator clients to sign messages, which are then aggregated and eventually verified efficiently in the distributed network, thus increasing the overall efficiency of the network. This completes our introduction to Phase 0 of Ethereum 2.0. In the next section, we explore features of Phase 1. Phase 1. The main feature of Phase 1 is shard chains. The specification is not fully complete yet, however, most of the details are complete. Shard chains. Shard chains are the main scalability feature that will initially consist of 64 chains and will grow over time as required. The main design goals in this phase revolve around creation, validation, and consensus of the data of shard chains. The state of each shard chain will be written periodically to the beacon chain. This is called a crosslink, which is a set of signatures from a set of validators, the committee that has attested to a block in a shard chain. This crosslink is included in the beacon chain representing the attestation of blocks of shard chains. The state is represented by the combined data Merkle root of the shard chain. The idea behind this mechanism is that when a block in the beacon chain is finalized, the corresponding block in the shard chain is also considered final. This way, other shards know that what the finalized block is and they can rely on that for further transactions across different shards. Cross-shard transactions. The agreement on each block's content is achieved by utilizing randomly selected shard validators by the beacon chain for each shard at each slot. A slot is defined as a period of time in which a block proposer proposes a block for attestation. A slot may be empty or filled with attested blocks. Slots are 12 seconds apart. A relevant concept is that of an epoch, which represents a number of slots, currently 32, after which validators are reshuffled in their validator sets, committees. The following diagram presents a process overview showing shards, the beacon chain, validators, the link with ETH1, and the phases of Ethereum 2.0. In Phase 1, there will be enhancements made to the Phase 0 design of the beacon chain to allow shard chains, transitioning from Ethereum 1 to Ethereum 2. Eventually, the aim is to transition completely into Ethereum 2.0. There are two options under discussion currently to achieve that: stateless clients and merging. Stateless clients. This is a proposal where Ethereum 1.0 clients will be transitioned into stateless clients. These rely on proofs from peers rather than stored copies of the chain state to verify blocks. The core idea behind this proposal is to trim the existing chain into digital receipts that prove the authenticity of the POW transactions. This option appears to be gaining more traction. Merging. This is a proposal where the Ethereum 1.0 chain will be merged into the Ethereum 2.0 beacon chain as is. The idea behind this proposal is to build interoperability bridges between Ethereum 1 and Ethereum 2 until Ethereum 2.0 is fully developed. A major feature of any blockchain is that it can run transactions on smart contracts. This feature will come with Phase 2 of Ethereum 2.0, which is responsible for state execution. Phase 2. Phase 2 is mainly concerned with state execution. Phase 2 will have the ability to run smart contracts and transactions on shard chains. In addition, constructs such as accounts will also be available with this phase. Each shard chain in Phase 2 will have its own EWASM EVM, which will allow for faster running of smart contracts. There is also a concept of the execution environment which allows shards in Phase 2 to build custom environments for specific use cases. This gives tremendous flexibility to developers as it allows them to build fully customized execution environments. It is quite early to say how exactly these execution environments will be designed because of the rapidly evolving research in this space. Phase 2 of Ethereum 2.0 will also focus on further scalability and continuous improvement of the protocol. There are many ideas including ZK Starks, ZK rollups, and commit chains. We will discuss scalability solutions in detail in Chapter 21, Scalability and Other Challenges. Phase 3. After Phase 2, further improvement and updates will continue. We can call this Phase 3. Next, let's have a look at the specific high-level architecture of Ethereum 2.0. Architecture. The following diagram shows the high-level architecture of Ethereum 2.0 clients and how they work together with the beacon chain. After completing the Running Ethereum 2.0 clients exercise in the book's online content repository, we'll be able to see the architecture shown in the following diagram in reality. The preceding diagram shows a validator node and a beacon node with their different services running on different ports. The structure of a beacon block is also shown on the left-hand side, including the fields of the block header and body as per the Phase 0 specifications. Now that we have a good understanding of Ethereum 2.0's design goals, its phases and architecture, you can put your new knowledge into practice. Doing so is out of the scope of this chapter, but by accessing this book's bonus content pages here. You can follow a start-to-finish demonstration of how an Ethereum 2.0 client can be installed and run on the Onyx testnet. Summary. In this chapter, we looked at Ethereum 2.0. We explored various aspects of its architecture and the overall vision behind the development of Ethereum 2.0. Currently, Ethereum 2.0 is under heavy development and only Phase 0, the beacon chain, is expected to launch in 2020. As the design Phase 0 is finalized, nothing much is expected to change with the production release of the beacon chain. The techniques and examples used in this chapter can be used for the production chain too, once it's available. We have also demonstrated in this book's bonus content pages, which we strongly encourage the reader to make use of, how to run Ethereum 2.0 beacon and validator clients. Remember that as the development of Ethereum 2.0 is rapidly evolving, some of the steps mentioned may change slightly, or the testnet that we used may be retracted. However, the steps are essentially the same. You may just have to slightly tweak the commands and run it on a different testnet. Readers are encouraged to keep an eye on prylabs.net for further developments. In the next chapter, we'll introduce Hyperledger, which is a very active and popular blockchain project upon which multiple blockchain projects are being built.
Chapter 17. Hyperledger. Hyperledger is not a blockchain, but a project that was initiated by the Linux Foundation in December 2015 to advance blockchain technology. This project is a collaborative effort by its members to build an open-source distributed ledger framework that can be used to develop and implement cross-industry blockchain applications and systems. The principal focus is to create and run platforms that support global business transactions. The project also focuses on improving the reliability and performance of blockchain systems. This chapter will, for the most part, discuss Hyperledger projects and their various features and components. As Hyperledger is so vast, it's not possible to cover all projects in detail in this short chapter. As such, we will introduce a variety of the projects available and then provide detailed discussions on two mainstream projects, Fabric and Sawtooth. Projects under the Hyperledger umbrella undergo multiple stages of development, going from proposal to incubation and eventually graduating to an active state. Projects can also be deprecated or put in an end-of-life state where they are no longer actively developed. For a project to be able to move into the incubation stage, it must have a fully working code base along with an active community of developers. The Hyperledger project currently has more than 300 member organizations and is very active with many contributors, and regular meetups and talks organized around the globe. We will first cover some of the various projects under Hyperledger. Then we will move on to examine the design, architecture, and implementation of two mainstream projects, Fabric and Sawtooth, in more detail covering the following topics on the way. Projects under Hyperledger: Hyperledger Reference Architecture, Hyperledger Fabric, Hyperledger Sawtooth, setting up a Sawtooth development environment. Projects under Hyperledger fall into different categories, and we'll start with the introduction of these categories in the next section. Projects under Hyperledger. There are 4 categories of projects under Hyperledger. Under each category, there are multiple projects. The categories are distributed ledgers, libraries, tools, domain-specific.
Currently, there are 6 distributed ledger projects under the Hyperledger umbrella: Fabric, Sawtooth, Iroha, Indy, Besu, and Burrow. Under libraries, there are the Aries, Transact, Quilt, and Ursa projects. The tools category of Hyperledger includes projects such as Avalon, Cello, Caliper, and Explorer. There are also domain-specific projects such as Hyperledger Grid and Hyperledger Labs. The following diagram visualizes the categorization of Hyperledger projects. A brief introduction to all of these projects follows. Distributed ledgers. Distributed ledgers, as we covered in Chapter 1, Blockchain 101, are a broad category of distributed databases that are decentralized, shared among multiple participants, and updatable only via consensus. Often, the terms blockchain and distributed ledger are used interchangeably. However, one key difference between distributed ledgers and blockchains is that blockchains are expected to have an architecture in which transactions are handled in batches of blocks, whereas distributed ledgers have no such requirements. All other attributes of distributed ledgers and blockchains are broadly the same. In Hyperledger, distributed ledger is a generic term used to denote both blockchains and distributed ledgers. Fabric. Hyperledger Fabric is a blockchain project that was proposed by IBM and Digital Asset Holdings, DAH. It is an enterprise-grade permission distributed ledger framework which provides a framework for the development of blockchain solutions and applications. Fabric is based on a modular and pluggable architecture. This means that various components such as the consensus engine and membership services can be plugged into the system as required. Currently, its status is active and it is the first project to graduate from incubation to active state. Sawtooth. Hyperledger Sawtooth is a blockchain project proposed by Intel in April 2016. It was donated to the Linux Foundation in 2016. Sawtooth introduced some novel innovations focusing on the decoupling of ledgers from transactions, flexible usage across multiple business areas using transaction families, and pluggable consensus. It is an enterprise-grade blockchain with a focus on privacy, security, and scalability. Ledger decoupling can be explained more precisely by saying that the transactions are decoupled from the consensus layer by making use of a new concept called transaction families. Instead of transactions being individually coupled with the ledger, transaction families are used, which allows more flexibility, rich semantics, and the open design of business logic. Transactions follow the patterns and structures defined in the transaction families. One of the innovative features that Intel has introduced with Hyperledger Sawtooth is a novel consensus algorithm called Proof of Elapsed Time, POET. It makes use of the Trusted Execution Environment, TEE, provided by Intel Software Guard Extensions, Intel SGX, to provide a safe and random leader election process. It supports both permissioned and permissionless setups. Iroha. Iroha was contributed by Soramitsu, Hitachi, NTT Data, and Kolu in September 2016. Iroha aims to build a library of reusable components that users can choose to run on their own Hyperledger-based distributed ledgers. Iroha's primary goal is to complement other Hyperledger projects by providing reusable components written in C++ with an emphasis on mobile development. This project has also proposed a novel consensus algorithm called Sumiraji, which is a chain-based Byzantine fault-tolerant consensus algorithm. Various libraries have been proposed and are being worked on by Iroha, including but not limited to a digital signature library, ED25519, a SHA-3 hashing library, a transaction serialization library, a P2P library, an API server library, an iOS library, an Android library, and a JavaScript library. Indy. This project is under incubation under Hyperledger. Indy is a distributed ledger developed for building decentralized identities. It provides tools, utility libraries, and modules which can be used to build blockchain-based digital identities. These identities can be used across multiple blockchains, domains, and applications. Indy has its own distributed ledger and uses redundant Byzantine fault-tolerant RBFT for consensus. Besu. Besu is a Java-based Ethereum client. It is the first project under Hyperledger that can operate on a public Ethereum network. Burrow. This project is currently in the incubation state. Hyperledger Burrow was contributed by Monax, who develop blockchain development and deployment platforms for business. Hyperledger Burrow introduces a modular blockchain platform and an Ethereum virtual machine (EVM)-based smart contract execution environment. Burrow uses proof-of-stake POS and a Byzantine fault-tolerant BFT tendermint consensus mechanism. As a result, Burrow provides high throughput and transaction finality. With this, we have completed an introduction to distributed ledger projects under Hyperledger. Let's now look at the next category, libraries. Libraries. A number of libraries are currently available under the Hyperledger project. This category includes projects that aim to support the blockchain ecosystem by introducing platforms for interoperability, identity, cryptography, and developer tools. We will now briefly describe each one of these. Aries. Aries is not a blockchain. In fact, it is an infrastructure for blockchain-rooted peer-to-peer interactions. The aim of this project is to provide code for P2P interactions, secrets management, verifiable information exchange, such as verifiable credentials, interoperability, and secure messaging for decentralized systems. The eventual goal of this project is to provide a dynamic set of capabilities to store and exchange data related to blockchain-based identity. Transact. Transact provides a shared library that handles smart contract execution. This library makes the development of distributed ledger software easier by allowing the handling of scheduling, transaction dispatch, and state management via a shared software library. It provides an approach to implement new smart contract development languages named smart contract engines. Smart contract engines implement virtual machines or interpreters for smart contract code. Two main examples of such engines are Ceph for EVM smart contracts and Sabre for WebAssembly WASM-based smart contracts. Quilt. This utility implements the Interledger protocol, which facilitates interoperability across different distributed and non-distributed ledger networks. Ursa. Ursa is a shared cryptography library that can be used by any project, Hyperledger or otherwise, to provide cryptography functionality. Ursa provides a C-Callable library interface and a Rust crate library. There are two sub-libraries available in Ursa, libUrsa and libZmix. libUrsa is designed for cryptographic primitives such as digital signatures, standard encryption schemes, and key exchange schemes. libZmix provides a generic method to produce zero-knowledge proofs. It supports signature proofs of knowledge, bullet proofs, range proofs, and set memberships. We've now covered 4 library projects currently available under Hyperledger. In the next section, we'll explore different tools that can be used in Hyperledger projects. Tools. There are a number of projects under the Tools category in Hyperledger. Tools under Hyperledger focus on providing utilities and software tools that help to enhance the user experience. For example, visualization tools such as blockchain explorers, deployment tools, and benchmarking tools fall into this category. We'll describe some of these briefly. Avalon. Avalon provides a trusted computer framework that enables privacy and allows off-chain processing of compute-intensive operations in a trusted and secure manner. It provides guarantee that a computation was performed correctly and privately. It also allows the improvement of scalability and performance and supports hardware-attested oracles. It is based on the Trusted Compute specifications published by the Enterprise Ethereum Alliance and is implemented as a separate project. Celo. The aim behind Celo is to allow the easy deployment of blockchains. This will provide an ability to allow as-a-service deployments of a blockchain service. Currently, this project is in the incubation stage. Caliper. Caliper is a benchmarking framework for blockchains. It can be used to measure the performance of any blockchain. There are different performance indicators supported in the framework. These include success rate, transaction read rate, throughput, latency, and hardware resource consumption, such as CPU, memory, and I/O. Ethereum, Fabric, Sawtooth, Burrow, and Iroha are currently the supported blockchains in Caliper. Explorer. This project aims to build a blockchain explorer for Hyperledger Fabric that can be used to view and query the transactions, blocks, and associated data from the blockchain. It also provides network information and the ability to interact with chain code. With this, we complete the introduction to the Hyperledger projects category of tools. Next, we'll introduce domain-specific projects. Domain-specific. Under Hyperledger, there are also some domain-specific projects that are created to address specific requirements. Currently, there are 2 projects under this category, which we will introduce now. Grid. Grid is a Hyperledger project that provides a standard reference implementation of supply chain-related data types, data models, and relevant business logic encompassing smart contracts. It is currently in the incubation stage. Labs. Hyperledger Labs provide a quick and easy way to start a project under Hyperledger without going through the official formal process of incubation and activation. This allows the development of research projects, hackathons, and demo projects. Each of the aforementioned projects is in various stages of development. This list is expected to grow as more and more members join the Hyperledger project and contribute to the development of blockchain technology. Now in the next section, we will examine the reference architecture of Hyperledger, which provides general principles and design philosophies that can be followed to build new Hyperledger projects. Hyperledger aims to build new blockchain platforms that are driven by industry use cases. As there have been many contributions made to the Hyperledger project by the community, the Hyperledger blockchain platform is evolving into a protocol for business transactions. Hyperledger is also evolving into a specification that can be used as a reference to build blockchain platforms as compared to earlier blockchain solutions that address only a specific type of industry or requirement. In the following section, a reference architecture model is presented that has been published by the Hyperledger project. This architecture can be used by a blockchain developer to build a blockchain that is in line with the specifications of the Hyperledger architecture. Hyperledger Reference Architecture. Hyperledger has published a white paper that presents a reference architecture model that can serve as a guide to build permissioned distributed ledgers. The reference architecture consists of various components that form a business blockchain. These high-level components are shown in the reference architecture diagram here, which has been drawn from the aforementioned white paper. In the preceding diagram, starting from the left, we see that we have 5 top-level components that provide various services. The first is identity, which provides authorization, identification, and authentication services under membership services. Then we have the policy component, which provides policy services. After this, we see blockchain and transactions, which consist of the consensus manager, distributed ledger, the network P2P protocol, and ledger storage services. The consensus manager ensures that the ledger is updatable only through consensus among the participants of the blockchain network. Finally, we have the smart contracts layer, which provides chain code services in Hyperledger and makes use of secure container technology to host smart contracts. Chain code can be considered as the Hyperledger equivalent of smart contracts. We will see all these in more detail in the Hyperledger Fabric section shortly. From a components perspective, Hyperledger contains various elements as described here. Consensus. These services are responsible for facilitating the agreement process between the participants on the blockchain network. Consensus is required to make sure that the order and state of transactions are validated and agreed upon in the blockchain network. Smart contracts. These services are responsible for implementing business logic as per the requirements of the users. Transactions are processed based on the logic defined in the smart contracts that reside on the blockchain. Communication. This component is responsible for message transmission and exchange between the nodes on the blockchain network. Security and crypto. These services are responsible for providing the capability to allow various cryptographic algorithms or modules to provide privacy, confidentiality, and non-repudiation services. Data store. This component provides an ability to use different data stores for storing the state of the ledger. This means that data stores are also pluggable, allowing the usage of any database backend, such as CouchDB or GoLevelDB. Policy services. This set of services provides the ability to manage the different policies required for the blockchain network. This includes endorsement policy and consensus policy. APIs and SDKs. This component allows clients and applications to interact with the blockchain. An SDK is used to provide mechanisms to deploy and execute chain code, query blocks, and monitor events on the blockchain. There are certain requirements of a blockchain service. In the next section, as an example, we are going to discuss the design goals of Hyperledger Fabric. Hyperledger Design Principles. There are certain requirements of a blockchain service. The reference architecture is driven by the needs and requirements raised by the participants of the Hyperledger project after studying the industry use cases. There are several categories of requirements that have been deduced from the study of industrial use cases and are seen as principles of design philosophy. We'll describe these principles in the following sections. Modular structure. The main requirement of Hyperledger is a modular structure. It is expected that a cross-industry blockchain will be used in many business scenarios, and as such, functions related to storage, policy, chain code, access control, consensus, and many other blockchain services should be modular and pluggable. The specification provided in the Hyperledger reference architecture suggests that the modules should be plug-and-play, and users should be able to easily remove and add a different module that meets the requirements of the business. Privacy and confidentiality. This is one of the most critical factors. As traditional blockchains are permissionless in a permission model, it is of the utmost importance that transactions on the network are visible to only those who are allowed to view it. The privacy and confidentiality of transactions and contracts are of absolute importance in a business blockchain. As such, Hyperledger's vision is to provide support for a full range of cryptographic protocols and algorithms. We discuss cryptography in Chapter 3, Symmetric Cryptography, and Chapter 4, Public Key Cryptography. It is expected that users will be able to choose appropriate modules according to their business requirements. For example, if a business blockchain needs to be run only between already trusted parties and performs very basic business operations, then perhaps there is no need to have advanced cryptographic support for confidentiality and privacy. Therefore, users should be able to remove that functionality module or replace it with a more appropriate module that suits their needs. Similarly, if users need to run a cross-industry blockchain, then confidentiality and privacy can be of paramount importance. In this case, users should be able to plug an advanced cryptographic and access control mechanism module into the blockchain, which can even allow the usage of hardware of security modules, HSMs. The blockchain should also be able to handle sophisticated cryptographic algorithms without compromising performance. In addition to the previously mentioned scenarios, due to regulatory requirements in business, there should also be a provision to allow the implementation of privacy and confidentiality policies in conformance with regulatory and compliance requirements. Identity. In order to provide privacy and confidentiality services, a flexible public key infrastructure (PKI) model that can be used to handle the access control functionality is also required. The strength and type of cryptographic mechanisms are also expected to vary according to the needs and requirements of the users. In certain scenarios, it might be required for a user to hide their identity, and as such, Hyperledger is expected to provide this functionality. Scalability. This is another major requirement that, once met, will allow reasonable transaction throughput, which will be sufficient for all business requirements and also a large number of users. Deterministic transactions. This is a core requirement in any blockchain. If transactions do not produce the same results every time they are executed, then regardless of who and where the transaction is executed, achieving consensus is impossible. Therefore, deterministic transactions become a key requirement in any blockchain network. We discussed these concepts in Chapter 10, Smart Contracts. Auditability. Auditability is another requirement of business hyperledgers. It is expected that an immutable audit trail of all identities, related operations, and any changes is kept. Interoperability. Currently, there are many blockchain platforms available, but they cannot communicate with each other easily. This can be a limiting factor in the growth of a blockchain-based global business ecosystem. It is envisaged that many blockchain networks will operate in the business world for specific needs, but it is important that they are able to communicate with each other. There should be a common set of standards that all blockchains can follow in order to allow communication between different ledgers. There are different efforts already underway to achieve this, not only under the Hyperledger umbrella such as Hyperledger Quilt, but also other projects such as Cosmos and Polkadot. Portability. The portability requirement is concerned with the ability to run across multiple platforms and environments without the need to change anything at the code level. Hyperledger Fabric, for example, is envisaged to be portable, not only at the infrastructure level, but also at the code, library, and API levels, so that it can support uniform development across various implementations of Hyperledger. Rich data queries. The blockchain network should allow rich queries to be run on the network. This can be used to query the current state of the ledger using traditional query languages, which will allow wider adoption and ease of use. All of the aforementioned points describe the general guiding principles that allow the development of blockchain solutions that are in line with the Hyperledger design philosophy. In the next section, we will look at Hyperledger Fabric in detail, which is the first project to graduate to the active status under Hyperledger. Hyperledger Fabric, or Fabric for short, is the contribution made initially by IBM and Digital Assets to the Hyperledger project. This contribution aims to enable a modular, open, and flexible approach toward building blockchain networks. Various functions in the Fabric are pluggable, and it also allows the use of any language to develop smart contracts. This functionality is possible because it is based on container technology, Docker, which can host any language. Chain code is sandboxed in a secure container, which includes a secure operating system, the chain code language, runtime environment, and SDKs for Go, Java, and Node.js. Other languages can be supported too in the future, if required, but this needs some development work. This ability is a compelling feature compared to domain-specific languages in Ethereum or the limited scripted language in Bitcoin. It is a permission network that aims to address issues such as scalability, privacy, and confidentiality. The fundamental idea behind this is modularization, which would allow flexibility in the design and implementation of the business blockchain. This can then result in achieving scalability, privacy, and other desired attributes and fine-tuning them according to requirements. Transactions in Fabric are private, confidential, and anonymous for general users, but they can still be traced back and linked to the users by authorized auditors. As a permissioned network, all participants are required to be registered with the membership services to access the blockchain network. This ledger also provided auditability functionality to meet the regulatory and compliance needs required by the user. Membership services. These services are used to provide access control capability for the users of the Fabric network. Membership services perform the following functions: user identity verification, user registration, assign appropriate permissions to the users depending on their roles. Membership services make use of a certificate authority, CA, in order to support identity management and authorization operations. This CA can be internal, such as Fabric CA, which is a default interface in Hyperledger Fabric, or an organization can opt to use an external certificate authority. Fabric CA issues enrollment certificates, eCerts, which are produced by an Enrollment Certificate Authority, ECA. Once peers are issued with an identity, they are allowed to join the blockchain network. There are also temporary certificates issued called T-certs, which are used for one-time transactions. All peers and applications are identified using a certificate authority. An authentication service is provided by the certificate authority. Membership service providers, MSPs, can also interface with existing identity services like LDAP. This section covered the membership services implemented in Hyperledger Fabric. Next, we'll introduce some of Fabric's blockchain services. Blockchain services. Blockchain services are at the core of Hyperledger Fabric. Components within this category are as follows. Consensus services. A consensus service is responsible for providing the interface to the consensus mechanism. This serves as a module that is pluggable and receives the transaction from other Hyperledger entities and executes them under criteria according to the type of mechanism chosen. Consensus in Hyperledger Fabric is implemented as a peer called orderer, which is responsible for ordering the transactions in sequence into a block. An orderer does not hold smart contracts or ledgers. Consensus is pluggable, and currently there are two basic types of ordering services available in Hyperledger Fabric. Solo. This is a basic ordering service intended to be used for development and testing purposes. Kafka. This is an implementation of Apache Kafka, which provides an ordering service. It should be noted that currently Kafka only provides crash fault tolerance, but does not provide Byzantine fault tolerance. This is acceptable in a permission network where the chances of malicious actors are almost none. In addition, there are also ordering services available in Hyperledger Fabric that are based on more familiar consensus mechanisms such as Raft and PBFT. Raft is a crash fault-tolerant and leader-follower based protocol for achieving distributed consensus. PBFT is a state machine replication-based BFT protocol that can be used in Hyperledger Fabric to achieve consensus. In addition to these mechanisms, other mechanisms may become available in the future that can be plugged into Hyperledger Fabric. Distributed ledger. Blockchain and world state are two main elements of the distributed ledger. Blockchain is simply a cryptographically linked list of blocks, as introduced in Chapter 1, Blockchain 101, and world state is a key value database. This database is used by smart contracts to store relevant states during execution by the transactions. A blockchain consists of blocks that contain transactions. These transactions contain chain code, which runs transactions that can result in updating the world state. Each node saves the world state on disk in level DB or couch DB, depending on the implementation. As Fabric allows pluggable data stores, you can choose any data store for storage. A block consists of three main components called block header, block data, transactions, and block metadata. The following diagram shows a blockchain depiction with the block and transaction structure in Hyperledger Fabric, with the relevant fields. Block header consists of three fields, namely number, data hash, and previous hash. Block data contains an ordered list of transactions. A transaction is made up of multiple fields such as transaction ID, previous transaction ID, channel ID, signatures, read-write sets, metadata, and many more. Block metadata mainly consists of the creator identity, time of creation, and relevant signatures. The peer-to-peer protocol. The P2P protocol in Hyperledger Fabric is built using Google RPC, gRPC. It uses protocol buffers to define the structure of the messages. Messages are passed between nodes in order to perform various functions. There are four main types of messages in Hyperledger Fabric: discovery, transaction, synchronization, and consensus. Discovery messages are exchanged between nodes when starting up in order to discover other peers on the network. Transaction messages are used to deploy, invoke, and query transactions, and consensus messages are exchanged during consensus. Synchronization messages are passed between nodes to synchronize and keep the blockchain updated on all nodes. Ledger storage. In order to save the state of the ledger by default, LevelDB is used, which is available at each peer. An alternative is to use CouchDB, which provides the ability to run rich queries. Now that we've established some of the core blockchain services used in Hyperledger Fabric, let's look at some of the chain code or smart contract services available, along with an overview of the APIs and CLIs available in Fabric. Smart contract services. These services allow the creation of secure containers that are used to execute the chain code. Components in this category are as follows. Secure container. Chain code is deployed in Docker containers that provide a lockdown sandbox environment for smart contract execution. Currently, Golang is supported as the main smart contract language, but any other mainstream languages can be added and enabled if required. Secure registry. This provides a record of all images containing smart contracts. Events. Events on the blockchain can be triggered by endorsers and smart contracts. External applications can listen to these events and react to them if required via event adapters. They are similar to the concept of events introduced in Solidity in Chapter 15, Introducing Web3. APIs and CLIs. An application programming interface provides an interface into Fabric by exposing various REST APIs. Additionally, command line interfaces that provide a subset of REST APIs and allow quick testing and limited interaction with the blockchain are also available. In the preceding sections, we have covered the main elements of Hyperledger Fabric's reference architecture. Next, let's consider a variety of Hyperledger Fabric's components from a network perspective. Components. There are various components that can be part of the Hyperledger Fabric blockchain. These components include, but are not limited to, the peers, clients, channels, world state database, transactions, membership service providers, smart contracts, and crypto service provider components. Peers. Peers participate in maintaining the state of the distributed ledger. They also hold a local copy of the distributed ledger. Peers communicate via Gossip Protocol. There are three types of peers in the Hyperledger Fabric network. Endorsing peers or endorsers, which simulate the transaction execution and generate a read-write set. Read is a simulation of a transaction's reading of data from the ledger, and write is the set of updates that would be made to the ledger if and when the transaction is executed and committed to the ledger. Endorsers execute and endorse transactions, It should be noted that an endorser is also a committer too. Endorsement policies are implemented with chain code and specify the rules for transaction endorsement. Committing peers or committers, which receive transactions endorsed by endorsers, verify them and then update the ledger with the read-write set. A committer verifies the read-write set generated by the endorsers along with transaction validation. Orderer nodes receive transactions from endorsers along with read-write sets, arrange them in a sequence and send them to committing peers. Committing peers then perform validation and committing to the ledger. All peers make use of certificates issued by membership services. Clients. Clients are software that make use of APIs to interact with Hyperledger Fabric and propose transactions. Channels. Channels allow the flow of confidential transactions between different parties on the network. They allow the use of the same blockchain network but with separate overlay blockchains. Channels allow only members of the channel to view the transactions related to them. All other members of the network will not be able to view the transactions. World State Database. World State reflects all the committed transactions on the blockchain. This is essentially a key value store that is updated as a result of transactions and chain code execution. For this purpose, either LevelDB or CouchDB is used. LevelDB is a key value store, whereas CouchDB stores data as JSON objects, which allows rich queries to run against the database. Transactions. Transaction messages can be divided into two types: deployment transactions and invocation transactions. The former is used to deploy new chain code to the ledger, and the latter is used to call functions from the smart contract. Transactions can be either public or confidential. Public transactions are open and available to all participants, while confidential transactions are visible only in a channel open to its participants. Membership Service Provider. The MSP is a modular component that is used to manage identities on the blockchain network. This provider is used to authenticate clients who want to join the blockchain network. A certificate authority is used in the MSP to provide identity verification and binding services. Smart contracts. We discuss smart contracts in detail in Chapter 10, Smart Contracts. In Hyperledger Fabric, the same concept of smart contracts is implemented, but they are called chain code instead of smart contracts. They contain conditions and parameters to execute transactions and update the ledger. Chain code is usually written in Golang or Java. Crypto Service Provider. As the name suggests, this is a service that provides cryptographic algorithms and standards for use in the blockchain network. This service provides key management, signature, and verification operations and encryption-decryption mechanisms. This service is used with the membership service to provide support for cryptographic operations for elements of blockchain such as endorsers, clients, and other nodes and peers. After this introduction to some of the components of Hyperledger Fabric, we will next see what an application looks like when on a Hyperledger network. Applications on blockchain. A typical application on Fabric is simply composed of a user interface, usually written in JavaScript, HTML that interacts with the backend chain code, smart contract stored on the ledger via an API layer. Hyperledger provides various APIs and command line interfaces to enable interaction with the ledger. These APIs include interfaces for identity, transactions, chain code, ledger, network, storage, and events. In the next section, we'll see how chain code is implemented. Chain code implementation. Chain code is usually written in Golang or Java. Chain code can be public, visible to all on the network, confidential, or access controlled. These code files serve as a smart contract that users can interact with via APIs. Users can call functions in the chain code that result in a state change, and consequently update the ledger. There are also functions that are only used to query the ledger and do not result in any state change. Chain code implementation is performed by first creating the chain code shim interface in the code. Shims provide APIs for accessing state variables and the transaction context of chain code. It can either be in Java or Golang code. The following 4 functions are required in order to implement the chain code. Init parentheses. This function is invoked when the chain code is deployed onto the ledger. This initializes the chain code and results in making a state change, which updates the ledger accordingly. Invoke parentheses. This function is used when contracts are executed. It takes a function name as parameters along with an array of arguments. This function results in a state change and writes to the ledger. Query parentheses. This function is used to query the current state of a deployed chain code. This function does not make any changes to the ledger. Main parentheses. This function is executed when a peer deploys its own copy of the chain code. The chain code is registered with the peer using this function. The following diagram illustrates the general overview of Hyperledger Fabric. Note that peer clusters at the top include all types of nodes, endorsers, committers, and orderers. The preceding diagram shows that peers, shown center top, communicate with each other and each node has a copy of blockchain. In the top right corner, the membership services are shown, which validate and authenticate peers on the network by using a CA. At the bottom of the diagram, a magnified view of blockchain is shown whereby existing systems can produce events for the blockchain and can also listen for the blockchain events, which can then optionally trigger an action. At the bottom right-hand side, a user's interaction with the application is shown. The application in turn interacts with the smart contract via the invoke parentheses method, and smart contracts can query or update the state of the blockchain. In this section, we saw how chain code is implemented and examined the high-level architecture of Hyperledger Fabric. In the next section, we will discuss the application model. The application model. Any blockchain application for Hyperledger Fabric follows the MVCB architecture. This is based on the popular MVC design pattern. Components in this model are view, control, model, data model, and blockchain. View logic. This is concerned with the user's interface. It can be a desktop, web application, or mobile front-end. Control logic. This is the orchestrator between the user's interface, data model, and APIs. Data model. This model is used to manage the off-chain data. Blockchain logic. This is used to manage the blockchain via the controller and the data model via transactions. After this brief introduction to the application model, let's move on to another important topic, consensus, which is important not only in Hyperledger Fabric, but is also central to blockchain design and architecture. Consensus in Hyperledger Fabric. The consensus mechanism in Hyperledger Fabric consists of 3 steps. Transaction endorsement. This process endorses the transactions by simulating the transaction execution process. Ordering. This is a service provided by the cluster of orderers, which takes endorsed transactions and decides on a sequence in which the transactions will be written to the ledger. Validation and commitment. This process is executed by committing peers, which first validate the transactions received from the orderers and then commit that transaction to the ledger. These steps are shown in the following diagram. The ordering step is also pluggable. There are a number of ordering services available for the Fabric consensus mechanism. Initially, in some versions of Fabric 1.0, only simple ordering services such as Apache Kafka were available. However, now, other advanced consensus algorithms such as the BFT Smart Honey Badger, and simplified BFT implementations are also available. In the next section, we'll describe how a transaction flows through various stages in Hyperledger Fabric before finally updating the ledger. The transaction lifecycle in Hyperledger Fabric. There are several steps that are involved in a transaction flow in Hyperledger Fabric. These steps are visualized in the following diagram. The steps are described in detail as follows. 1. Transaction proposal by clients. This is the first step where a transaction is proposed by the clients and sent to endorsing peers on the distributed ledger network. All clients need to be enrolled via membership services before they can propose transactions. 2. The transaction is simulated by endorsers, which generates a read-write set. This is achieved by executing the chain code, but instead of updating the ledger, only an RW set depicting any reads or updates to the ledger is created. 3. The endorsed transaction is sent back to the application. 4. The endorsed transactions and RW sets are submitted to the ordering service by the application. 5. The ordering service assembles all endorsed transactions and RW sets in order into a block and sorts them by channel ID. 6. The ordering service broadcasts the assembled block to all committing peers. 7. Committing peers validate the transactions. 8. Committing peers update the ledger. 9. Finally, notification of success or failure of the transaction by committing peers is sent back to the client's applications. The following diagram represents the aforementioned steps and the Fabric architecture from a transaction flow perspective. As you can see in the preceding diagram, the first step is to propose transactions, which a client does via an SDK. Before this, it is assumed that all clients and peers are registered with the membership service provider. So far, we have covered the core architecture of Hyperledger Fabric 1.0. This architecture works well but requires some improvements. In order to address these limitations, a new version of Hyperledger Fabric, Fabric 2.0, has been developed. In the next section, we will introduce the core features of Fabric 2.0. Fabric 2.0. This is a major upgrade to the protocol. The fundamentals remain the same, but some very interesting new features and improvements have been made, which are introduced in the following sections. New chain code lifecycle management. In Hyperledger Fabric 2.0, a new decentralized chain code lifecycle management is implemented, which is the main notable difference between Fabric 1.0 and Fabric 2.0. In the former, an organization administrator can install the chain code in its own organization, and other organizations' administrators have to unconditionally agree to instantiate, deploy, or upgrade the chain code. In other words, there is no agreement process between organizations to agree on the installation of a chain code. This problem is resolved by introducing checks, which enables peers to only participate in a chain code if their organizational administrators have agreed to it. Now let's look at the chain code lifecycle in Fabric 1.0. 1. Each organization administrator installs chain code on their peers. 2. An administrator instantiates the code by deploying or upgrading. 3. After results are received, the transaction is submitted to the orderers. 4. After ordering, it is submitted to all peers and committed. Now we'll look at Fabric 2.0's lifecycle, which highlights the differences between it and Fabric 1.0. 1. Install chain code by putting the package on the file system. Each organization administrator installs chain code on their peers. 2. Provide approval by executing the approve form y.org function. This verifies that the organization agrees with the chain code definition. 3. Send the ordering service to the orderer. 4. Commits to the organization collection. The collection is a private data collection that provides a mechanism to allow private data sharing only between those organizations that are party to the transaction. even if they are within the same channel. In other words, collections allow private data sharing between a subset of organizations on a channel. Even though other organizations are members of the same channel, they cannot see the data shared between a subset of organizations that are sharing data using collection, also called private data collection. 5. Other organizations' administrators perform the same steps 1 to 4. 6. After these steps are executed, there is a record in each organization indicating the agreement on the chain code definition. 7. Define the chain code as per the agreement in step 6. 8. Submit to ordering. 9. Commit to the definition of all peers. 10. The organization administrator who committed the chain code definition now invokes the init function on its own peers and other organizations' peers. 11. Submit to ordering. 12. Commit all the peers. In addition to the chain code lifecycle management changes in Fabric 2.0, there are also new chain code application patterns. We will introduce these next. New chain code application patterns. There are also new chain code application patterns introduced in Fabric 2.0 for collaboration and consensus. These are automated checks that can be added by an organization to enable additional validation before a transaction is endorsed. In addition, decentralized agreement is also supported where multiple organizations can propose conditions for an agreement, and when those conditions are met, a collective agreement can be made on a transaction. Enhanced data privacy. Fabric 2.0 enhances data privacy by introducing collection-level endorsement policies per organization collections and the flexible sharing and verification of private data. External chain code launcher. In Hyperledger Fabric 2.0 by default, Docker APIs are used to build and run chain code. In addition, external builders and launchers can be used if required. In previous versions, there was a requirement to have access to the Docker daemon to build and run chain code. But in Fabric 2.0, there is no such dependency. There is also no requirement to run chain code in Docker containers anymore. Chain code can be run in any environment deemed appropriate by the network operator. Raft Consensus. Raft is a crash fault-tolerant CFT ordering service for achieving consensus. It is based on the etcd library and is based on a leader-follower model. In this model, a leader is elected whose decision is then replicated by its followers. Better performance. In Fabric 2.0, caching has been introduced at the CouchDB state database level to improve performance by reducing the read latency introduced due to expensive lookup operations in previous versions. With this section, our introduction to Hyperledger Fabric is complete. Hyperledger Fabric is the flagship project of Hyperledger and is used in a wide variety of applications. A list of cross-industry projects built with Hyperledger Fabric and other Hyperledger projects is being maintained here. Readers can explore this further to understand how Hyperledger Fabric is used in different use cases. Hyperledger Fabric is continually evolving and more features and changes are expected in future releases. However, no major design changes are expected since the introduction of version 2.0. In the next section, we'll explore another popular Hyperledger project named Sawtooth. Hyperledger Sawtooth. Sawtooth is an enterprise-grade distributed ledger that can run in both permissioned and non-permissioned modes. Sawtooth has several new features, which are introduced in the following sections. Core features. These features include modular design, parallel transaction execution, global state agreement, dynamic consensus, and some other advanced features. We will now explore these features one by one. Modular design. The modular design of Sawtooth enables separation between the application and the core system. This means that developers can focus on the business objectives instead of worrying about the underlying design of the system. The design of Sawtooth can be viewed as a layered architecture where transaction processors manage the application business logic, and on another layer, validators handle the verification and consensus on transactions. A separate layer called the transaction processing layer is responsible for managing transaction rules, permissions, and consensus-related settings. In summary, Sawtooth separates the core functionality of blockchain from the business logic. Parallel transaction execution. Usually blockchains process transactions sequentially. This serial processing is seen as a bottleneck and impacts performance, which makes some blockchains unsuitable for high-throughput use cases. Sawtooth has come up with a remarkable feature in which an advanced parallel scheduler splits the transactions into parallel flows, which results in increased performance due to the parallel execution of transactions. Global State Agreement. Sawtooth ensures that each node has an identical copy of the blockchain database, and this database is also cryptographically verifiable. This means that Sawtooth is a cryptographically verifiable distributed ledger with global state agreement. Dynamic and pluggable consensus algorithms. Sawtooth supports different types of consensus mechanism via a modular mechanism implemented as a separate process. A very interesting feature of Sawtooth is that consensus mechanisms can be changed while a blockchain is running. This means that a different consensus mechanism can be chosen for the same blockchain, regardless of what was initially chosen at the network setup. This is a powerful feature that is made possible due to the isolation between the consensus mechanism and transaction semantics. Multi-language support. Blockchain applications in Sawtooth can be written using various different languages. Sawtooth also includes SDKs for different languages, such as JavaScript, Python, and Go. This feature makes it a flexible choice for many developers. Enhanced Event Mechanism. Sawtooth supports the creation and broadcasting of events where applications can subscribe to blockchain-related events or application-specific events. Also, it can relay information about the execution of a transaction to clients without the requirement to store that data in a state. On-chain governance. Sawtooth allows the on-chain storage, management, and application of configuration settings and permissions, which makes it easier for all clients to refer to a single source of configuration. Interoperability. Sawtooth supports integration with other blockchain technologies. For example, it introduced a project named Seth, which allows EVM-based smart contracts to be deployed on Sawtooth. Sawtooth has proposed some other novel features, such as the introduction of a new consensus algorithm called POET, and the idea of transaction families. We'll discuss these concepts in more detail in the upcoming sections. Consensus in Sawtooth. Sawtooth supports several types of algorithms. A novel mechanism introduced with Sawtooth is called POET. POET is a trusted, executed, environment-based lottery function that elects a leader randomly based on the time a node has waited for a block proposal. POET is a novel consensus algorithm that allows a node to be selected randomly based on the time that the node has waited before proposing a block. This concept is in contrast to other leader election and lottery-based proof-of-work algorithms, such as the POW used in Bitcoin, where an enormous amount of electricity and computer resources are used in order to be elected as a block proposer. POET is a type of POW algorithm, but instead of spending computer resources, it uses a trusted computing model to provide a mechanism to fulfill the POW requirements. POET makes use of Intel's SGX architecture, software guard extensions to provide a T to ensure the randomness and cryptographic security of the process. It should be noted that the current implementation of Hyperledger Sawtooth does not require real hardware SGX-based T, as it is simulated for experimental purposes only and, as such, should not be used in production environments. The fundamental idea in POET is to provide a mechanism of leader election by waiting randomly to be elected as a leader for proposing new transactions. POET, however, has a limitation, which has been highlighted by Itay Eyal. This limitation is called the stale chip problem. This limitation results in hardware wastage, which can result in the waste of resources. The stale chip problem revolves around the idea that it is financially beneficial for malicious actors to collect lots of old SGX chips, which will increase their chances of becoming the miner of the next block. Note that they can collect lots of old SGX chips to build mining rigs serving only one purpose of mining, instead of buying modern CPUs with SGX, which will not only serve in POET consensus but will also be useful for other general computation. Instead, they can choose to just collect as many old SGX-enabled chips as they can and increase their chances of winning the mining lottery. Also, old SGX-enabled CPUs are cheap and can result in the increased use of old inefficient CPUs. It is similar to Bitcoin miners racing to get as many fast ASICs as possible to increase their chances of becoming the miner. It results in hardware wastage. There is also the possibility of hacking the chip's hardware. If an SGX chip is compromised, the malicious node can win the mining round every time, which results in complete system compromise and undeserved incentivizing of miners. This problem is also called the broken chip problem. As demonstrated next, there are two types of POET consensus, one with Intel SGX and another without SGX, along with a development mode mechanism. POET CFT. POET CFT makes use of a simulated SGX environment. It is not dependent on hardware and can run on any processor. It is only CFT and not BFT. POET SGX. This is an SGX-dependent consensus mechanism. It provides BFT tolerance and consumes very little CPU processing power. Dev mode. As the name suggests, this is a development mode consensus mechanism that is suitable for testing transaction processors with single validator deployments. This is not intended for production usage. It makes use of a simple random leader election algorithm for development and testing. Other consensus mechanisms include PBFT and Raft. PBFT. PBFT is a leader-based Byzantine fault-tolerant consensus mechanism. This is a commonly used protocol for consortium networks, and many newer BFT protocols are based on this protocol. We discussed PBFT in detail in Chapter 5, Consensus Algorithms. Raft. Raft is a comparatively faster algorithm than POET. It is a CFT algorithm that works in a leader-follower fashion where a leader is elected for a period, term of arbitrary time. It has immediate finality due to a lack of forks. There is another consensus type called quorum voting, which is an adaptation of consensus protocols built by Ripple and Stellar. This consensus algorithm allows instant transaction finality, which is usually desirable in permission networks. In this section, we have looked at the core feature of Sawtooth and explored various consensus mechanisms that Sawtooth supports. In the next section, we'll look at how transactions are generated and processed in Sawtooth. Just like any other blockchain in Sawtooth, transactions follow a protocol and a lifecycle. We will explore that in the next section. Transaction lifecycle. Before describing the transaction flow, let's define what a transaction is. It is a function that, when executed, results in changing the state of the blockchain. Transactions are always made part of a batch, even if there is only one transaction in a batch. Validators receive these batches for processing. Now that we understand what a transaction is, let's explore how a transaction flows in a Sawtooth network. 1. A client submits a transaction to a validator. This is usually achieved by utilizing the REST API available with the validator. By default, port TCP 8008 is exposed, where REST API is available. 2. After the transaction is submitted, it is propagated across the validator network. 3. One of the validators is elected as a leader, which then creates a candidate block and publishes it on the network. 4. This candidate block is propagated across the entire validator network. 5. When validators receive this block, it is validated. In addition, transaction processors validate and execute all transactions present in the candidate block. 6. Once the block is validated and verified, it is written in its respective local storage and the state is updated accordingly. This process can be visualized using the following diagram. Note that the smaller node displays on the right are identical to the main node display on the center left. Having understood the transaction flow in Sawtooth, let's explore in more detail what components Sawtooth is made up of and how are they interconnected. Components. A Sawtooth node is composed of several components. A Sawtooth network is composed of several Sawtooth nodes. A generic Sawtooth node architecture and a network are shown in the following diagram. Note that the smaller node displays on the right are identical to the main node display on the center left. At a fundamental level, a Sawtooth node contains a validator, REST API, consensus engine, and transaction processors. We will introduce each one of these concepts and their purpose in the following sections. Validators. The validator is the component that is responsible for validating batches of transactions. It combines transactions into blocks and maintains consensus on the Sawtooth blockchain network. In addition, validators also perform coordination functions between clients, transaction processors, and other validators on the network. Validators communicate using the Gossip Protocol. REST API. REST API is responsible for providing a communication interface between clients and validators. REST APIs are available by default over TCP 8008. Client. The client is responsible for implementing the client logic. It is responsible for the following functions: transaction creation and payload generation, the handling of events in the blockchain and application, such as error handling, notifications, and blockchain state updates, displaying data to the users. State. The state in a blockchain is represented as a log of all changes made to the blockchain database since the start of the blockchain network or genesis block. All nodes in the Sawtooth network, just like any other blockchain, keep a local copy of the state database. The state is updated as a result of transaction execution, and when new blocks are produced, each validator updates its local state database accordingly. The global state, on the other hand, represents the agreement on the state of the blockchain between all nodes on the network. Transaction processors. Transaction processors are responsible for validating transactions and updating the state. State update and transaction validation is performed based on the rules defined in the associated transaction family. There is always a transaction family associated with the transaction processor. For example, there is a small bank transaction family for the small bank _TP transaction processor. In summary, transaction processors are responsible for transaction validation, block creation, business logic, or transaction rules. Transaction processors implement the business logic for a transaction family or Sawtooth application. A transaction processor is responsible for transaction validation and state transition and updates governed by the rules defined in the Sawtooth application. We will now explore the concept of a transaction family in detail. Transaction families. A traditional smart contract paradigm provides a solution that is based on a general-purpose instruction set for all domains. For example, in the case of Ethereum, a set of opcodes has been developed for the EVM that can be used to build smart contracts to address any type of requirements for any industry. While this model has its merits, it is becoming clear that this approach is not very secure, as it provides a single interface into the ledger with a powerful and expressive language, which potentially offers a larger attack surface for malicious code. This complexity and generic virtual machine paradigm have resulted in several vulnerabilities that were found and exploited recently by hackers. A recent example is the DAO hack and further denial of services (DOS) attacks that exploited limitations in some EVM opcodes. The DAO hack was discussed in Chapter 10, Smart Contracts. A model shown in the following figure describes the traditional smart contract model, where a generic virtual machine has been used to provide the interface into the blockchain for all domains. In order to address this issue, Sawtooth has proposed the idea of transaction families. A transaction family is created by decomposing the logic layer into a set of rules and a composition layer for a specific domain. The key idea is that business logic is composed within transaction families, which provides a more secure and powerful way to build smart contracts. Transaction families contain the domain-specific rules and another layer that allows the creation of transactions for that domain. Another way of looking at it is that transaction families are a combination of a data model and a transaction language that implements a logic layer for a specific domain. The data model represents the current state of the blockchain ledger, whereas the transaction language modifies the state of the ledger. It is expected that users will build their own transaction families according to their business requirements. The following diagram represents this model, where each specific domain such as financial services, digital rights management (DRM), supply chain, and the health industry has its own logic layer comprised of operations and services specific to that domain. This makes the logic layer both restrictive and powerful at the same time. Transaction families ensure that operations related to only the required domain are present in the control logic, thus removing the possibility of executing needless, arbitrary, and potentially harmful operations. Sawtooth has provided several transaction families as examples. Each transaction family is identified by a name and has an associated transaction processor. The following table will explore these in detail. A transaction family encompasses application-specific business logic. This business logic defines various transaction types or operations that are permitted on the blockchain. Transaction families keep the transaction rules separate from the Sawtooth core blockchain functionality. From an implementation point of view, transaction families implement data models and transaction languages for an application. A transaction family includes the following elements: a transaction processor, which defines the business logic for the application. A transaction processor performs the following functions: registration with the validator, handling of transaction payloads, state update and retrieval as required. A data model, which performs the following functions: records data, stores data, defines valid operations, specifies data for the application payload. A client, which is responsible for the following functions: handling the client logic for the application, creating and signing for the transactions, creating batches of the transactions, submitting transaction batches to the validator. Transaction family is a new concept introduced with Hyperledger Sawtooth. It is a set of operations or types of transactions or a category of transactions that represent specific requirements of use case. A data model and transaction language for specific applications are both implemented in a transaction family. Next, we will introduce REST APIs, which provide an API interface between a client and a transaction processor. REST API. This is an optional component that runs as a service on a validator node, which facilitates communication between a client and a transaction processor. A REST API can also run as a separate system. Now that we've covered theoretical aspects and understand the Sawtooth architecture, let's introduce a practical example, which will help to better understand the theory covered so far. Setting up a Sawtooth development environment. In this section, an introduction is given on how to set up a development environment for Sawtooth. There are a few prerequisites that are required in order to set up the development environment. The easiest way to get Sawtooth up and running is by using Docker. In the following example, we will set up a 5-node network using Docker. Prerequisites. For this process, you'll need to first install Docker. In this example, we are using $docker-v. Sawtooth supports different consensus algorithms. In this example, we will use POET. However, other options are available too, such as PBFT. The YAML configuration files for both of these options are available at the links in the following sections. Using POET. The following link is available to download the YAML file for setting up Sawtooth with the POET consensus algorithm. https://sawtooth.hyperledger.org/docs/1-2/app_default-poet.yml. Using PBFT, here you can access the YAML file for setting up Sawtooth with PBFT consensus. https://sawtooth.hyperledger.org/docs/core/nightly/1-developers_guide/sawtooth-developers_pbft.yml. Setting up a Sawtooth network. In this section, we will see how a Sawtooth network can be created. First, we start with creating a directory, and then we will download specific configuration files which will help with the configuration of the network. 1. Create a directory named Sawtooth. 2. Change the directory to Sawtooth. 3. Download the POET YAML file. This command will show an output like the following, indicating that the sawtooth-default-poet.yml file has been downloaded successfully. Note that only the final part of the output is shown for brevity. 4. Start the network. This will show a long output and will take several minutes to complete. The output will be similar to the following, which shows the progress of the process. 5. Once the network is started up successfully, we can verify that all the components are up by simply checking it in the Docker dashboard, as shown in the following screenshot. 6. Confirm that the REST API is running by issuing the following command to connect to the REST API container on a node. This will open a prompt like the following. 7. Issue the command as shown here. This will show an output similar to the following, showing that a process is running for the REST API. Network functionality can be verified by using the following commands. 8. Connect to the shell container. This will open a prompt like the one shown here. 9. Check whether the peers are up. This will produce the following output, which displays the list of peers on the network. 10. Another way to find peers is to use the sawtooth command. This command shows an output similar to the following. It shows the list of peers indicating the protocol used, the name of the validator, and the port. 11. The peer list can also be retried using this command. This command will show the output shown here, which shows that there are other validators available and running. 12. Similarly, the block list can also be retrieved. This command will produce the following output, listing the height, ID, and previous hash of the blocks for node 0. 13. We can also view the sawtooth settings as shown in the following command. This command shows all the settings of the blockchain. 14. The block list can also be retrieved using the command shown here. The output of this command displays the number, block IDs, batches, transactions, and the signer. 15. Specific blocks can be queried using the command. This will show an output similar to the one shown here. The output is truncated for brevity. This output shows the block structure with several fields including the header, transactions, state root hash, and many more. In this section, we have seen how to set up a sawtooth network and perform queries to find various pieces of information about the network, such as a list of peers and information about blocks and the blockchain. With this, a basic introduction to Sawtooth is complete. Sawtooth and Hyperledger in general are very large subjects and cannot be explained entirely in a single chapter. However, this chapter will serve as a solid foundation for further study. Summary. In this chapter, we have gone through an introduction to the Hyperledger project. Firstly, the core ideas behind the Hyperledger project were discussed, and a brief introduction to all projects under Hyperledger was provided. Two main Hyperledger projects were discussed in detail, namely Hyperledger Fabric and Sawtooth. All these projects are continuously improving and changes are expected in the next releases. However, the core concepts of all the projects mentioned previously are expected to remain unchanged or change only slightly. Readers are encouraged to visit the relevant links provided in the chapter to see the latest updates. It is evident that a lot is going on in this space, and projects like Hyperledger from the Linux Foundation are playing a pivotal role in the advancement of blockchain technology. Each of the projects discussed in this chapter has novel approaches toward solving the issues faced in various industries, and any current limitations from the blockchain technology are also being addressed, such as scalability and privacy. It is expected that more projects will soon be proposed to the Hyperledger project, and it is envisaged that with this collaborative and open effort, blockchain technology will advance tremendously and collectively benefit the community as a whole. In the next chapter, we will discuss tokenization, which is one of the most prominent applications of blockchain technology and is disrupting many industries, especially the financial industry.
Chapter 18. Tokenization. A token is a representation of an object. We use tokens in many different fields, including economics and computing. In daily life, tokens have been used to represent something of value, such as a gift voucher that is redeemable in exchange for items. In computing, different types of tokens are used, which can be defined as objects that represent eligibility to perform some operation. For example, an access token is used to identify a user and its privileges on a computer system. A hardware security token is used in computer systems to provide a means to authenticate a user, verify their identity to a computer system. Tokens are also used in computer security mechanisms to substitute sensitive data with non-sensitive equivalents to prevent direct access to sensitive information. For example, in mobile payment systems, tokens are used to safeguard credit card information, which is represented by a token on the mobile device instead of the actual credit card data. Just like the general use of tokens in day-to-day life, in the blockchain world, tokens also represent something of value. However, the critical difference is that token exists digitally on a blockchain and is operated cryptographically, which means that they are generated, protected, and transferred using cryptographic protocols. Now that we understand what a token is, we can define tokenization as a process that converts an asset to a digital token on a blockchain. Specifically, it is a process of converting the ownership rights of a real-world asset into a cryptographic digital token on a blockchain. In this chapter, we will cover blockchain tokens or crypto tokens and tokenization. We will use the term token from now on to represent tokens on a blockchain. We will also cover different types of tokens, relevant standards, tokenization platforms, applications of tokenization, and a practical example of how to develop tokens on Ethereum. A guide to the specific topics we will cover in this chapter is provided here. Tokenization on the blockchain, types of token, token offerings, token standards, trading and finance, DeFi,
building an ERC20 token, emerging concepts. Now we'll begin our discussion on tokenization in the context of blockchain, which is the main aim of this chapter. Tokenization on a blockchain. Tokenization in the context of blockchain is the process of representing an asset digitally on a blockchain. It can be used to represent commodities, real estate, ownership of art, currency, or anything else of value. After this brief definition, let's explore how tokenization can be beneficial. Advantages of tokenization. Tokenization provides several benefits, including faster transaction processing, flexibility, low cost, decentralization, security, and transparency. The following are some of the most important of these benefits. Faster transaction processing. As transactions and all relevant parties are present on the blockchain and readily available, there is no need to wait for a response from a counterparty or to wait for clearing and settlement operations. All these operations can be performed efficiently and quickly on a blockchain. Flexibility. Due to the worldwide adoption of systems that use tokens such as payment systems, tokenization becomes simple due to easier cross-border use. Low cost. In comparison with traditional financial products, tokenization requires a lower cost to implement and incurs a lower cost to the end user due to digitization. Generally, in finance, we have seen that digitization, starting from the introduction of digital accounts in the 1960s, has led to more efficient and cheaper financial systems. More recently, the introduction of digital payments has revolutionized the financial industry. In the same spirit, tokenization using blockchain can be considered another step toward achieving further efficiency and cost reduction. In fact, tokenization gives rise to a better, more efficient, and more democratic financial system. For example, just being able to share customer data recorded on one blockchain across all financial institutions reduces costs. Similarly, the possibility of converting illiquid assets into liquid assets is another way of increasing efficiency and profits. Decentralization. Tokens are presented on a public blockchain, leveraging the decentralization offered by blockchain technology. However, in some cases, a level of somewhat acceptable centralization is introduced due to the control and scrutiny required by investors and exchanges and other involved and interested parties. Security. As tokens are cryptographically protected and produced using a blockchain, they are secure. However, note that proper implementation must use good practice and meet established security industry standards. Otherwise, security flaws may result in exploitation by hackers, leading to financial loss. Transparency. Because they are on a blockchain, tokens are more transparent than traditional financial systems, meaning that any activity can be readily audited on a blockchain and is visible to everyone. Trust. As a result of the security and transparency guarantees, more trust is naturally placed in tokenization by investors. Fractional ownership. Imagine a scenario in which you own a painting by Vincent van Gogh. It is almost impossible in traditional scenarios to have multiple owners of the painting without immense legal, financial, and operational challenges. However, on a blockchain using tokens, any asset, such as our Van Gogh painting, can be fractionalized in such a way that it can be owned in part by many investors. The same situation is true for a property. If I wanted to have shared ownership with someone, it requires complicated legal procedures. However, with tokenization, fractional ownership of any asset, be it art, real estate, or any other off-chain real-world asset, is quick, easy, efficient, secure, and a lot less complicated than traditional methods. Low entry barrier. Traditional financial systems require traditional verification mechanisms, which can take a long time for a customer. While they are necessary and serve the purpose in traditional financial systems, these processes take a long time due to the necessary verification processes and the involvement of different entities. However, on a blockchain, this entry barrier is lowered because there is no need to go through the long verification checks. This is because not only is tokenization based on cryptographic guarantees provided by the blockchain, but for many decentralized applications, the apps in this ecosystem, it is basically just a matter of downloading a DApp on your mobile device, depositing some funds if required, and becoming part of the ecosystem. Innovative applications. Tokenization has resulted in many innovative applications, including novel lending systems on blockchain, insurance, and other numerous financial applications, including decentralized exchanges. Securities can now be tokenized and presented on blockchain, which results in client trust and satisfaction because of the better security and faster processing times. An example of this innovation is DeFi, which we will discuss later on in the chapter. More liquidity. This is due to the easy availability and accessibility of the tokens for the general public. By using tokens, even illiquid assets such as paintings can be tokenized and traded on an exchange with fractional ownership. With all these advantages, there are, however, some issues that must be addressed in the tokenization ecosystem. We'll discuss these next. Disadvantages of tokenization. In this section, we present some of the disadvantages of tokenization. At the top of the list, we have regulatory requirements. Regulatory issues. Regulation is a crucial subject of much debate. It is imperative that the tokens are regulated so that investors can have the same level of confidence that they have when they invest using traditional financial institutions. The big issue with tokenization and generally any blockchain technology is that they are mostly decentralized, and in cases where no single organization is in control, it becomes quite difficult to hold someone responsible if something goes wrong. In a traditional system, we can go to the regulatory authorities or the relevant ombudsman services, but who is held responsible on a blockchain? Some of this situation has changed with recent security tokenization standards and legislation, which consider tokens as securities. This means that security tokens will then be treated as securities, and the same legal, financial, and regulatory implications will be placed on these tokens that are applicable in the currently established financial industry. Refer to sec.gov/answers/about-laws shtml.html, where different laws that govern the securities industry are presented. This helps to increase customer confidence levels and trust in the system. However, there are still many challenges that need to be addressed. A new type of financial crime might be evolving with this tokenization ecosystem where, instead of using well-known and researched traditional financial fraud methods, criminals may choose to launch a technically sophisticated attack. For an average user, this type of attack is difficult to spot and understand as they are entirely on a blockchain and digitized. New forms of front-running and market skewing on decentralized finance platforms is increasingly becoming a concern. Legality of tokens. This is a concern in some jurisdictions where tokens and cryptocurrency are illegal to own and trade. Technology barrier. Traditional financial systems have been the norm with brick-and-mortar banks. We are used to that system, but things have changed and are expected to change rapidly with tokenization. Tokenization-based financial ecosystems are easier to use for a lot of people, but for some, technological illiteracy can become an issue and could become a barrier. Sometimes the interfaces and software applications required to use tokenization platforms, such as trading platforms, are difficult to use for an average user. Security issues. The underlying blockchain technology is considered solid from a security point of view. and it is boasted sometimes that due to the use of cryptography, it is impossible to launch attacks and commit fraud on a blockchain. However, this is not entirely true, even with the firm security foundation that blockchains provide. The way tokenization platforms and the apps are implemented on the blockchain result in security issues that can be exploited by hackers, potentially leading to financial loss. In other words, even if the underlying blockchain is relatively secure, the tokenization the app implemented on top may have vulnerabilities that could be exploited. These weaknesses could have been introduced by poor development practices or inherent limitations in the still evolving smart contract languages. In this section, we have looked at some of the pros and cons of tokenization. Next, let's look at some of the many types of token. Naturally, the way tokenization has been evolving in the last few years, there are now new and different types of tokens that are present in the ecosystem. Types of tokens. With the rapid development of blockchain technology and the related applications, there has been a tremendous increase in the development of various types of token and relevant ecosystems. First, let's clarify the difference between a coin and token. Is a Bitcoin a token, or are tokens and coins the same thing? A coin is a native token of a blockchain. It is the default cryptocurrency of the blockchain on which it runs. Common examples of such a token are Bitcoin and Ether. Both of these tokens or coins have their own native blockchain on which they run, the Bitcoin blockchain and the Ethereum blockchain. On the other hand, a token is a representation of an asset that runs on top of a blockchain. For example, Ethereum not only has its own Ether cryptocurrency as a native token or coin, but also has thousands of other tokens that are built on top of Ethereum for different applications. Thanks to its support of smart contracts, Ethereum has become a platform for all sorts of different types of tokens, ranging from simple utility tokens to game tokens and high-value, application-specific tokens. Now that we understand the difference between a coin and a token, let's have a look at the usage and significance of different types of tokens. Tokens can be divided broadly into two categories based on their usage: fungible tokens and non-fungible tokens. Fungible tokens. From an economics perspective, fungibility is the interchangeability of an asset with other assets of the same type. For example, a 10-pound note is interchangeable with a different 10-pound note or two 5-pound notes. It does not matter which specific denominations they are, as long as they are of the same type, pound, and have same value, the sum of two 5-pound notes. The notes are acceptable. Fungible tokens work on the same principle. They are indistinguishable. Tokens of the same type are indistinguishable from each other. In other words, they are identical. Interchangeable. A token is fully interchangeable with another token of the same value. Divisible. Tokens are divisible into smaller fractions. Non-fungible tokens. Let's consider non-fungible tokens, NFTs, also called Nifty, with the help of an example. We saw that fungibility allows the same types of token to be interchangeable, but non-fungible tokens are not interchangeable. For example, a collectible painting is a non-fungible asset, as it cannot be replaced with another painting of the same type and value. Each painting is unique and distinguishable from others. Non-fungible tokens are unique. Non-fungible tokens are unique and different from other tokens of the same type or in the same category. Non-interchangeable. Since they are unique and represent specific attributes, these tokens are not interchangeable with tokens of the same type. For example, a rare painting is unique due to its attributes and is not interchangeable with another, even an exact-looking replica. We can also think about the certificate of authenticity that comes with a rare painting, that is also non-interchangeable with another due to its unique attributes representing the rare art. Indivisible. These tokens are available only as a complete unit. For example, a college diploma is a unique asset distinguishable from other diplomas of the same type. It is associated with a unique individual and is thus not interchangeable, and it is not rational for it to be divided into fractions, making it indivisible. In the next section, we introduce another interesting topic, stable tokens, which are a different type of token with interesting properties that make them more appealing to some investors. Stable tokens. Stable tokens or stable coins are a type of token that has its value pegged to another asset's value, such as fiat currencies or precious metals. Stable tokens maintain a stable price against the price of another asset. Bitcoin and other similar cryptocurrencies are inherently volatile and experience dramatic fluctuations in their price. This volatility makes them unsuitable for usual, everyday use. Stable tokens emerged as a solution to this limitation in tokens. The price stability is maintained by backing the token up by a stable asset. This is known as collateralization. Fiat currencies are stable because they are collateralized by some reserve, such as foreign exchange, forex reserves, or gold. Moreover, sound monetary policy and regulation by authorities play a vital role in the stability of a currency. Tokens or cryptocurrencies lack this type of support and thus suffer from volatility. There are 4 types of stable coin. Fiat collateralized. These stable coins are backed by a traditional fiat currency such as US dollars. Fiat collateralized coins are the most common type of stable coins. Some of the common stable coins available today are Gemini Dollar, GUSD, Paxos, PAX, and Libra. Commodity collateralized. As the name suggests, these stable coins are backed up by fungible commodities, assets such as oil or gold. Common examples of such tokens are Digix Gold tokens and Tether Gold. Crypto collateralized. This type of stable coin is backed up by another cryptocurrency. For example, the DAI stablecoin accepts Ethereum-based assets as collateral in addition to soft pegging to the US dollar. Algorithmically stable. This type of stable token is not collateralized by a reserve but stabilized by algorithms that keep track of market supply and demand. For example, Basecoin can have its value pegged against the US dollar. A basket, a financial term for group or collection of similar securities, of assets, or an index, and it also depends on a protocol to control the supply of tokens based on the exchange rate between itself and the peg used, such as the US dollar. This mechanism helps to maintain the stability of the token. Security tokens. Security tokens derive their value from external tradable assets. For example, security tokens can represent shares in a company. The difference is that traditional securities kept in a bank register and traded on traditional secondary markets, whereas security tokens are available on a blockchain. Being securities, they are governed by all traditional laws and regulations that apply to securities. But due to their somewhat decentralized nature, in which no middleman is required, security tokens are seen as a more efficient, scalable, and transparent option. Now that we have covered different types of token, let's see how an asset can be tokenized by exploring the process of tokenization. Process of tokenization. In this section, we'll present the process of tokenization, discuss what can be tokenized, and provide a basic example of the tokenization of assets. Almost any asset can be tokenized and presented on a blockchain, such as commodities, bonds, stocks, real estate, precious metals, loans, and even intellectual property. Physical goods that are traditionally illiquid in nature, such as collectibles, intellectual property, and art, can also be tokenized and turned into liquid tradable assets. A generic process to tokenize an asset, or in other words, offer a security token, is described here. Note that there are many other technical details and intricacies involved in the process that we are skipping for brevity. The first step is to onboard an investor who is interested in tokenizing their asset. The asset that is presented for tokenization is scrutinized and audited, and ownership is confirmed. This audit is usually performed by the organization offering the tokenized security. It could be an exchange or a cryptocurrency startup. The process of tokenized security starts, which leads to the security token offering, STO. The physical asset is placed with a custodian in the real world for safekeeping. The derivative token representing the asset is created by the organization offering the token and issued to investors through a blockchain. Traders start to buy and sell these tokens using trading exchanges in a secondary market, and these trades are settled. The buyer makes a payment and receives the goods on a blockchain. Common platforms for tokenization include Ethereum and EOS. Tezos is also emerging as another platform for tokenization due to its support for smart contracts. In fact, any blockchain that supports smart contracts can be used to build tokens. At this point, a question arises about how all these different types of token reach the general public for investment. In the next section, we examine how this is achieved by first explaining what token offerings are and examining the different types. Token offerings. Token offerings are mechanisms to raise funds and profit. There are a few different types of token offerings. We will introduce each of these separately now. One main common attribute of each of these mechanisms is that they are hosted on a blockchain and make use of tokens to facilitate different financial activities. These financial activities can include crowdfunding and trading securities. Initial coin offerings. Initial coin offering or initial currency offering, ICO, is a mechanism to raise funds using cryptocurrencies. ICOs have been a very successful but somewhat controversial mechanism for raising capital for new cryptocurrency or token projects. ICOs are somewhat controversial sometimes due to bad design or poor governance. But at times, some of the ICOs have turned out to be outright scams. A list of fraudulent schemes is available at cryptochainuni.com/scam-list. These types of incidents have contributed toward the bad reputation and controversy of ICOs in general. While there are some scams, there are also many legitimate and successful ICOs. The return on investment, ROI, for quite a few of ICOs has been quite big and has contributed toward the unprecedented success of many of these projects. Some of these projects include Ethereum, NXT, NEO, IOTA, and Qtum. A common question is asked here regarding the difference between the traditional initial public offerings, IPOs, and ICOs, as both of these mechanisms are fundamentally designed to raise capital. The difference is simple. ICOs are blockchain-based token offerings that are usually initiated by startups to raise capital, by allowing investors to invest in their startup. Usually, in this case, contributions by investors are made using already existing and established cryptocurrencies, such as Bitcoin or Ether. As a return, when the project comes to fruition, the initial investors get their return on the investment. On the other hand, IPOs are traditional mechanisms used by companies to distribute shares to the public. This is done using the services of underwriters, which are usually investment banks. IPOs are only usually allowed for those companies who are already well established, but ICOs, on the other hand, can be offered by startups. IPOs also offer dividends as returns, whereas ICOs offer tokens that are expected to rise in value once the project goes live. Another key comparison is that IPOs are regulated, traditional mechanisms that are centralized in nature, while ICOs are decentralized and unregulated. Because ICOs have been unregulated, which has resulted in a number of scams and people losing their money. Another form of fundraising, known as security token offerings, was introduced. We'll discuss this next. Security token offerings. Security token offerings, STOs, are a type of offering in which tokenized securities are traded at cryptocurrency exchanges. Tokenized securities or security tokens can represent any financial asset, including commodities and securities. The tokens offered under STOs are classified as securities. As such, they are more secure and can be regulated, in contrast with ICOs. If an STO is offered on a traditional stock exchange, then it is known as a tokenized IPO. Tokenized IPO is another name for an STO that is used when an STO is offered on a regulated stock exchange, which helps to differentiate between an STO offered on a traditional regulated exchange and one that is offered on cryptocurrency exchanges. STOs are regulated under the Markets in Financial Instruments Directive, MiFID II in the European Union. Initial exchange offerings. Initial exchange offering, IEO, is another innovation in the tokenization space. The key difference between an IEO and ICO is that in an ICO, the tokens are distributed via crowdfunding mechanisms to investors' wallets. But in an IEO, the tokens are made available through an exchange. IEOs are more transparent and credible than IEOs due to the involvement of an exchange and due diligence performed by the exchange. Equity token offerings. Equity token offerings, ETOs, are another variation of ICOs and STOs. ICOs offer utility tokens, whereas equity tokens are offered in ETOs. When compared with STOs, ETOs offer shares of a company, whereas STOs offer shares in any asset, such as currencies or commodities. From this point of view, ETOs can be regarded as a specific type of STO, where only shares in a company or venture are represented as tokens. Decentralized Autonomous Initial Coin Offering. Decentralized Autonomous Initial Coin Offering, DAICO, is a combination of decentralized autonomous organizations, DAOs, and ICOs that enables investors to have more control over their investment and is seen as a more secure, decentralized, and automated version of ICOs.
Other token offerings. Different variations of ICOs and new concepts are being introduced quite regularly, and innovation is only expected to grow in this area. A comparison of different types of token offering is presented in the following table. With all these different types of tokens and associated processes, a need to standardize naturally arises so that more adoption and interoperability can be achieved. To this end, several development standards have been proposed, which we discuss next. Token standards. With the advent of smart contract platforms such as Ethereum, it has become quite easy to create a token using a smart contract. Technically, a token or digital currency can be created on Ethereum with a few lines of code, as shown in the following example. The preceding code works and can be used to create and issue tokens. However, the issue is that without any standard mechanism, everyone would implement tokenization smart contracts in their own way based on their requirements. This lack of standardization will result in interoperability and usability issues, which obstructs the widespread adoption of tokenization. To remedy this, the first tokenization standard was proposed on Ethereum, known as ERC20. ERC20 is the most famous token standard on the Ethereum platform. Many token offerings are based on ERC20, and there are wallets available such as MetaMask that support ERC20 tokens. ERC20 was introduced in November 2015, and since then has become a very popular standard for fungible tokens.
There are almost 1,000 ERC20 tokens listed on Etherscan, which is a clear indication of this standard's popularity. It has been used in many ICOs and has resulted in valuable digital currencies, tokens, over the last few years, including EOS, Golem, and many others. While ERC20 defined a standard for fungible tokens and was widely adopted, it has some flaws, which results in some security and usability issues. For example, a security issue in ERC20 results in the loss of funds if the tokens are sent to a smart contract that does not have the functionality to handle tokens. The effectively burned tokens result in a loss of funds for the user. To address these shortcomings, ERC-223 was proposed. ERC-223 ERC-223 is a fungible token standard. One major advantage of ERC-223 as compared to ERC-20 is that it consumes only 50% of ERC-20's gas consumption, which makes it less expensive to use on Ethereum mainnet. ERC-223 is backward compatible with ERC-20 and is used in a number of major token projects such as Link and CN Exchange, CNEX. ERC-777 The main aim of ERC-777 is to address some of the limitations of ERC-20 and ERC-223. It is backward compatible with ERC-20. It defines several advanced features to interact with ERC-20 tokens. It allows sending tokens on behalf of another address, contract, or account. Moreover, it introduces a feature of hooks, which allows token holders to have more control over their tokens. ERC-721 ERC-721 is a non-fungible token standard. ERC-721 mandates a number of rules that must be implemented in a smart contract for it to be ERC-721 compliant. These rules govern how these tokens can be managed and traded. ERC-721 was made famous by the CryptoKitties project. CryptoKitties is a blockchain game that allows players to create, breed, and trade different types of virtual cats on the blockchain. Each kitty is unique and tradable for a value on the blockchain. ERC-884 This is the standard for ERC-20, compliant shared tokens that are conformant with Delaware Generation Corporation's law. ERC-1400 This is a security token standard that defines how to build, issue, trade, and manage security tokens. It is also referred to as ERC-1411, after it was renamed from ERC-1400. Under ERC-1400, there are a few other standards, which are as follows. ERC-1410, a partially fungible token standard that defines a standard interface for grouping an owner's tokens into partitions. ERC-1594, this defines a core security token standard. ERC-1643, this is the document management standard. ERC-1644, this is the token controller operation standard. ERC-1066, this standard specifies a standard way to design Ethereum status codes. The aim of ERC-1400 and the standards within it is to cover all activities related to the issuance, management, control, and processing of security tokens. ERC-1404. This ERC standard allows the issuance of tokens with regulatory transfer restrictions. These restrictions enable users to control the transfer of tokens in different ways. For example, users can control when, to whom, and under what conditions the tokens can be transferred. For example, an issuer can choose to issue tokens only to a whitelisted recipient or check whether there are any timing restrictions on the sender's tokens. ERC-1404 introduces two new functions in the ERC-20 standard to introduce restriction and control mechanisms. These two functions are listed as follows. With this, we have completed our introduction to ERC standards. Now let's have a quick introduction to finance and financial markets. This will provide a foundation for the material presented next, such as DeFi, as many of the terms and ideas are the same, albeit in a different context. Trading and finance. Before we move on to exploring one of the largest ecosystems based on tokenization, decentralized finance, DeFi, let's first look at some traditional finance and trading concepts. This will provide a solid foundation for the material presented in the next section and will cover token trading and related concepts such as decentralized exchanges and asset tokenization. Financial markets. Financial markets enable the trading of financial securities such as bonds, equities, derivatives, and currencies. There are broadly three types of markets: money markets, credit markets, and capital markets. Money markets are short-term markets where money is lent to companies or banks for interbank lending. Foreign exchange or Forex is another category of money markets where currencies are traded. Credit markets consist mostly of retail banks who borrow money from central banks and loan it to companies or households in the form of mortgages or loans. Capital markets facilitate the buying and selling of financial instruments, mainly stocks and bonds. There are many types of financial instruments such as cash instruments, derivative instruments, loans, securities, and many more. Securitization is the process of creating a new security by transforming illiquid assets into tradable financial instruments. Capital markets can be divided into two types: primary and secondary markets. Stocks are issued directly by the companies to investors in primary markets, whereas in secondary markets, investors resell their securities to other investors via stock exchanges. Various electronic trading systems are used by exchanges today to facilitate the trading of financial instruments. Trading. A market is a place where parties engage in exchange. It can be either a physical location or an electronic or virtual location. Various financial instruments, including equities, stocks, foreign exchanges, commodities, and various types of derivatives, are traded at these marketplaces. Recently, many financial institutions have introduced software platforms to trade various types of instruments from different asset classes. Trading can be defined as an activity in which traders buy or sell various financial instruments to generate profit and hedge risk. Investors, borrowers, hedgers, asset exchangers, and gamblers are a few types of traders. Traders have a short position when they owe something. In other words, if they have sold a contract, they have a short position. When traders buy a contract, they have a long position. There are various ways to transact trades, such as through brokers or directly on an exchange or over-the-counter (OTC), where buyers and sellers trade directly with each other instead of using an exchange. Brokers are agents who arrange trades for their customers and act on a client's behalf to deal at a given price or the best possible price. Exchanges. Exchanges are usually considered to be very safe, regulated, and reliable place for trading. During the last decade, electronic trading has gained popularity over traditional floor-based trading. Now traders send orders to a central electronic order book from which the orders, prices, and related attributes are published to all associated systems using communications networks, thus in essence creating a virtual marketplace. Exchange trades can be performed only by members of the exchange. To trade without these limitations, the counterparties can participate in OTC trading directly. Orders and order properties. Orders are instructions to trade, and they are the main building blocks of a trading system. They have the following general attributes: the instrument's name, the quantity to be traded, direction, buy or sell, the type of the order that represents various conditions. For example, limit orders and stop orders. Orders are traded by bid prices and offer prices. Traders show their intention to buy or sell by attaching bid and offer prices to their orders. The price at which a trader will buy is known as the bid price. The price at which a trader is willing to sell is known as the offer price. Order management and routing systems. Order routing systems route and deliver orders to various destinations depending on the business logic. Customers use them to send orders to their brokers, who then send these orders to dealers, clearinghouses, and exchanges. There are different types of orders. The two most common ones are market orders and limit orders. A market order is an instruction to trade at the best price currently available in the market. These orders get filled immediately at spot prices. On the other hand, a limit order is an instruction to trade at the best price available, but only if it is not lower than the limit price set by the trader. This can also be higher depending on the direction of the order, either to sell or buy. All of these orders are managed in an order book, which is a list of orders maintained by the exchange, and it records the intention of buying or selling by the traders. A position is a commitment to sell or buy a number of financial instruments, including securities, currencies, and commodities for a given price. The contracts, securities, commodities, and currencies that traders buy or sell are commonly known as trading instruments, and they come under the broad umbrella of asset classes. The most common classes are real assets, financial assets, derivative contracts, and insurance contracts. Components of a trade. A trade ticket is the combination of all of the details related to a trade. However, there is some variation depending on the type of the instrument and the asset class. These elements are described here. The underlying instrument. The underlying instrument is the basis of the trade. It can be a currency, a bond, an interest rate, a commodity, or an equity. The attributes of financial instruments are discussed here. General attributes. This includes the general identification information and essential features associated with every trade. Typical attributes include a unique ID, an instrument name, a type, a status, a trade date, and a time. Economics. Economics are features related to the value of the trade. For example, the buy or sell value, ticker, exchange price, and quantity. Sales. Sales refers to the sales characteristic, related details such as the name of the salesperson. It is just an informational field, usually without any impact on the trade lifecycle. Counterparty. The counterparty is an essential component of a trade as it shows the other side, the other party involved in the trade of the trade, and it is required to settle the trade successfully. The normal attributes include the counterparty name, address, payment type, any reference IDs, settlement date, and delivery type. Trade lifecycle. A general trade lifecycle includes the various stages from order placement to execution and settlement. This lifecycle is described step by step as follows. Pre-execution. An order is placed at this stage. Execution and booking. When the order is matched and executed, it is converted into a trade. At this stage, the contract between counterparties is matured. Confirmation. This is where both counterparties agree to the particulars of the trade. Post-booking. This stage is concerned with various scrutiny and verification processes required to ascertain the correctness of the trade. Settlement. This is the most vital part of the trade life cycle. At this stage, the trade is final. End-of-day processing. End-of-day processes include report generation, profit and loss calculations, and various risk calculations. This life cycle is also shown in the following image. In all of the aforementioned processes, many people and business functions are involved. Most commonly, these functions are divided into functions such as front office, middle office, and back office. In the following section, we introduce some terminology that's relevant to crimes that occur in the financial industry. Order anticipators. Order anticipators try to make a profit before other traders can carry out trading. This is based on the anticipation of a trader who knows how the activities of other traders will affect prices. Front runners, sentiment-oriented technical traders, and squeezers are some examples of order anticipators. Market manipulation. Market manipulation is strictly illegal in many countries. Fraudulent traders can spread false information in the market, which can then result in price movements, enabling illegal profiteering. Usually, manipulative market conduct is trade-based, and it includes generalized and time-specific manipulations, actions that can create an artificial shortage of stock, an impression of false activity, and price manipulation to gain criminal benefits are included in this category. Both of these terms are relevant to financial crime. However, it is possible to develop blockchain-based systems that can thwart market abuse due to its transparency and security properties. Now that we have gone through some basic financial and market concepts, let's dive into decentralized finance. DeFi. DeFi stands for Decentralized Finance, which is the largest application of tokenization. It is an ecosystem that has emerged as a result of the development of many different types of financial applications built on top of blockchains. With blockchains being decentralized and the applications being related to finance, the term emerged as decentralized finance, or DeFi for short. DeFi is an umbrella term used to describe a financial services ecosystem that is built on top of blockchains. Centralized finance, or CeFi for short, is a term now used to refer to the traditional financial services industry, which is centralized in nature, while DeFi is a movement to decentralize the traditional centralized financial services industry. Tokenization plays a vital role in the DeFi ecosystem, which is the largest use of tokenization. DeFi is a vast subject with many different applications, protocols, assets, tokens, blockchains, and smart contracts. The DeFi ecosystem is the fastest growing infrastructure running on different blockchains. Most DeFi applications are running on Ethereum, but some are also running on EOS. The range of DeFi dApps includes, but is not limited to lending and borrowing, trading, asset management, insurance, tokenization, and prediction markets. All these decentralized applications, along with their smart contracts and infrastructure, make up the DeFi ecosystem. In DeFi and in blockchain-based trading systems in general, the trading of tokens is the prime activity. We briefly describe this next. Trading tokens. Tokens can be traded on exchanges. With the advent of DeFi, now decentralized exchanges are also emerging, abbreviated as DEX. DEXs are decentralized and therefore require no central authority or intermediary to facilitate trading. Traders can trade with each other directly on a peer-to-peer basis. One of the advantages of DEXs due to decentralization is that traders are not required to transfer their funds to an intermediary. Instead, funds can remain under their own control, and they can directly trade with another counterparty without the involvement of an intermediary. While the entry barrier to DEX is low due to a lack of traditional Know Your Customer (KYC) requirements, this also makes them risky for investors because if somehow the DEX is hacked, then there is no protection against loss of funds. Some examples of DEXs are Uniswap, Bancor, Waves DEX, and iDEX. This ecosystem is growing at a very fast pace and is only expected to grow further. With all this activity in token trading, some malpractices are expected. In order to control these and ensure a fair and just system, regulation, which we'll discuss next, plays a vital role. Regulation. Regulation of tokens is an important subject. In the last few years, especially after a wave of scam ICOs, there is genuine interest in protecting the investor. Due to this, many regulatory authorities have issued warnings and guidelines around ICOs, and some have also issued directives mandating the process of issuing and managing tokens. We will cover regulation in a bit more detail in Chapter 21, Scalability and Other Challenges. Now, after all this theoretical background, let's see how a token can be built on Ethereum. We will build our own ERC20 compliant token called MyERC20 token, or MET for short. Building an ERC20 token. In this section, we will build an ERC20 token. In previous chapters, we saw several ways of developing smart contracts, including writing smart contracts in Visual Studio Code and compiling them and then deploying them on a blockchain network. We also used the Remix IDE, Truffle, and MetaMask to experiment with various ways of developing and deploying smart contracts. In this section, we will use a quick method to develop, test, and deploy our smart contract on a Goerli test network. We will not use Truffle or Visual Studio Code in this example as we have seen this method before. We are going to explore a quicker method to build and deploy our contract. In this example, we will see how quickly and easily we can build and deploy our own token on the Ethereum blockchain network. Prerequisites. We will use the following components in our example. Remix IDE available at remix.ethereum.org. Note that in the following example, the user interface and steps required might be slightly different depending on the stage of development. This is because Remix IDE is under heavy development, and new features are being added to it at tremendous pace. As such, some changes are expected in the user interface too. However, the fundamentals are not expected to change and no major changes are expected in the user interface. MetaMask, which we installed in Chapter 12, Further Ethereum, we used it again in Chapter 16, Serenity, to deploy a contract on a Goerli test network, and we will use the same network in this example. You can create a new account if required. Building the Solidity contract. Now let's start writing our code. First, we explore what the ERC20 interface looks like, and then we will start writing our smart contract step by step in the Remix IDE. The ERC20 interface defines a number of functions and events that must be present in an ERC20 compliant smart contract. Some more rules that must be present in an ERC20 compliant token are listed here. Total supply. This function returns the number of the total supply of tokens. Balance of. This function returns the balance of the token owner. Transfer. This function takes the address of the recipient and a specified value as a number of tokens and transfers the amount to the address specified. Transfer from. This function takes from sender's address to recipient's address and value amount as parameters and returns true or false. It is used to transfer funds from one account to another. Approve. This function takes spender, recipient, and value number of tokens as parameters and returns a boolean true or false as a result. It is used to authorize the spender's address to make transfers on behalf of the token owner up to the approved amount, value. Allowance. This function takes the address of the token owner and the spender's address and returns the remaining number of tokens that the spender has approval to withdraw from the token owner. There are three optional functions which are listed as follows. Name. This function returns the name of the token as a string. It is defined in code as follows. Symbol. This returns the symbol of the token as a string. It is defined as follows. Decimals. This function returns the number of decimals that the token uses as an integer. It is defined as follows. Finally, there are two events that must be present in an ERC20 compliant token. Transfer. This event must trigger when tokens are transferred, including any zero-value transfer. The event is defined as follows. Approval. This event must trigger when a successful call is made to the approve function. The event is defined as follows. Now let's have a look at the source code of our ERC20 token. This is written in Solidity, which we are familiar with and have explored in detail in Chapter 14, Development Tools and Frameworks. Solidity Contract Source Code. The source code for our ERC20 token is as follows. Let's explain this code step by step, before writing it into the Remix IDE. First is the Solidity compiler and language version. The first line of the code specifies the compiler version using the pragma directive for which our program is written. Then we create the contract object. After this, the contract object is defined with the name myERC20token. Then we have the mappings. These are the two mappings used in the ERC20 smart contract. The first one is for keeping balances and the other one is used for allowances. These are the state variables. They describe the name, symbol, and decimal precision points and the total supply of our token. This is the transfer event. It has three parameters, from, to, and value. From represents the address from which the tokens are coming. To is the account to which tokens are being transferred, and value is the number of tokens. This is the approval event. This has three parameters, owner address, recipient address, and value. The index keyword allows us to search for a specific log item instead of searching through all logs. It enables log filtration to search and extract only the required data instead of returning all logs. This is the constructor that is executed when the contract is created. It is optional in Solidity and is used to run initialization code. In our example, the initialization code contains the statements to transfer the entire balance, total supply, to the creator of the smart contract. In our case, it is the sender's account. It also then emits the transfer event indicating that the transfer has taken place from address 0 to msg.sender, our contract creator, and total supply, which is 100 in our case, just to keep things simple. This is the total supply function. This function returns the total amount of tokens after deducting it from the balance of the account. This is the balance of function. The balance of function returns the balance of the token owner. The allowance function is as follows. The allowance function returns the total remainder of the tokens. This is the transfer function which returns true or false depending on the result of the execution. The require convenience function is used to check for certain conditions and throw an exception if the conditions are not met. In our example, this checks whether the value exceeds the sender's balance, and if it does, an error message will be generated stating that value exceeds sender's balance. If this check passes, the transfer occurs, and after emitting the transfer event, the function returns true, indicating the successful transfer of tokens. This is the approve function, which returns true or false depending on the result of the execution of the function. This function takes spender, the user, and value, number of tokens, as arguments and serves as a mechanism to provide approval to the user to require the allowed number of tokens from our ERC20 contract. This function is the transfer from function, which can be used to automate the transfer of tokens from one address to another. It takes three parameters, from, to, and value. It returns true or false depending upon the execution of the function. First, with the require functions, the balance and allowances are checked to ensure that enough balance and allowance is available. After that, the transfer occurs and eventually the transfer event is emitted, followed by a true Boolean value returned by the function indicating the successful transfer. Now that we understand what our source code does, the next step is to write it in the Remix IDE and deploy it. Deploying the contract on the Remix JavaScript virtual machine. In this step, we simply take the source code and write or simply paste it in the Remix IDE. Once pasted, this code will look like this. To achieve this, begin by opening the Remix IDE. When the Remix IDE opens up, it will show an interface similar to the following. Select Solidity under Environments, as we are going to write smart contracts using the Solidity smart contract language. After selecting the Solidity environment, create a new file by choosing the File Explorers option from the list of icons on the left-hand side, and add a new file by clicking the plus sign. Create a new file in the Remix IDE named erc20example.sol. When we have created the new file, it will look like the following screenshot. Now simply write the source code in the IDE or paste it directly. The next step is to compile the source code. To do this, click on Compile erc20example.sol. Optionally, Auto-Compile can also be selected under Compiler Configuration, which will compile the code automatically as soon as it is written into the IDE. Once compiled successfully, it is ready to be deployed. First, we will deploy it on JavaScript VM available with the Remix IDE to ensure that everything works. Once we have tested that it can be deployed correctly and works as per our expectations, we could deploy it on the mainnet using MetaMask. In our example, however, we will deploy it on the Goerli testnet using MetaMask. Remember that we have some Ether left from our exercise in Chapter 16, Serenity, and have a test account on the Goerli network. We can use the same account for this example, or create a new account and fund it using the process in Chapter 16, Serenity. The aim of this exercise is to understand how MetaMask can be used to deploy our new token smart contract on an Ethereum network. We will also see how we can import ERC20 tokens in MetaMask and use it to transfer funds from one account to another. After compilation, we deploy the smart contract using the Deploy and Run Transactions interface available within the Remix IDE. This is shown in the following screenshot. Make sure the environment JavaScript VM is selected and an account is selected from which to deploy, and then select Deploy. Once it's deployed, we will see an output similar to the following screenshot, where the contract will become available under Deployed Contracts, and in the logs, we can see relevant details regarding the deployment of the contract. Most importantly, we can see in the logs that when the contract is created, the first event emitted is transfer. Here we can see that all 100 tokens have been transferred to the owner account. Once it's deployed, we will see under Deployed Contracts all the functions exposed by the contract in the Remix IDE. We can test the functionality of our contract using this interface. For example, calling total supply shows a value of 100, which indicates the number of tokens, and calling symbol shows the string met, our token symbol. At this point, our contract works and we have tested it locally. Now we can deploy it onto the Goerli testnet. We will use MetaMask for this purpose. In the Remix IDE under Deploy and Run Transactions, select the Injected Web3 option, as shown in the following screenshot. This is the execution environment that is provided by enabling Web3 within the browser using the MetaMask plugin. First, confirm that MetaMask is running and connected to the Goerli test network. This should be easy to check as we used this same network in Chapter 16, Serenity. If everything is working in MetaMask, it should display a screen similar to the following screenshot. Note that you may have to log in again to MetaMask. Once you're logged in, select the Goerli network and an account that has some Ether in it. In the Remix IDE, choose Injected Web3 in the Environment field under Deploy and Run Transactions. This is shown in the following screenshot. Note that in the screenshot, the Goerli 5 network is selected. It also shows the account that we have set up in MetaMask. Now we are all set to deploy this on the Goerli test network. Click Deploy, which will open the MetaMask window to confirm the transaction, as shown here. Click Confirm and the contract will be deployed. We can see this in the history in MetaMask as shown here. Similar to the test that we did earlier in this example when we deployed our contract on the JavaScript VM, we can invoke different functions exposed by our new ERC20 token directly from the Remix IDE, as shown here. We can also see our token on the Etherscan token tracker. This is shown by accessing the following link. The Etherscan page can also be seen in the following screenshot. So, here we have it, our own MET token deployed on the Goerli test network. Now, if desired, we could deploy this to the Ethereum mainnet provided that we have some Ether available. We can perform exactly the same steps to deploy it, with the only difference being that in MetaMask we will choose the Ethereum mainnet as the network. Adding tokens in MetaMask. Once we have deployed our contract and our ERC20 token is now on the blockchain, so to speak, unless we are able to view it and perform operations on it, the token on its own is of no real use. To perform operations on the token, we can manually create commands using the web3.js send_raw_transaction method, and use the JavaScript and command line geth console to interact with it. Alternatively, we can use an easier option and simply add the token to a wallet. Wallets abstract away the complexities associated with transaction creation and management and provide an easy-to-use interface to perform transfers and similar tasks. MetaMask can serve as a wallet for tokens and provides an interface to add tokens. In this section, we'll see how we can add our MET token to MetaMask and perform some operations on it. Open MetaMask and find the Add Token option, either on the main user interface or open the account menu and it will display the current account as shown here. Click on Add Token and select Custom Token. Enter the contract address, which will automatically display the token symbol and the decimal points as shown in the following screenshot. Press Next and then confirm that you want to add these tokens, as shown here. Now we have 100 MET in our MetaMask wallet. Now let's send 10 MET to another account on the Goerli network. Click on Send, then enter the target's account's details. Enter 10 MET and click Next. Click Confirm and the transaction will be processed. We can see this transfer on Etherscan here. This page is also shown in the following screenshot. Now, coming back to the Remix IDE, we can now see that our balance has been reduced by 10 MET. Similarly, we can check the balance of the target account to which we transferred 10 MET, which is now 10 MET. We can see all the transfers of our ERC20 token, MET here on Etherscan. This page can also be viewed in the following screenshot. With this, we have covered how to create an ERC20 token from scratch and deploy it on the Ethereum blockchain. Let's now have a look at some of the novel concepts that are emerging due to the remarkable success of tokenization and the blockchain ecosystem in general. Emerging concepts. With the advent of blockchain and tokenization, several new concepts have emerged over the last few years. We will introduce some of them now. Tokenomics, token economics. Tokenomics or token economics is an emerging discipline that is concerned with the study of economic activity, economic models, and the impact of tokenization. It deals with the goods and assets that have been tokenized and the entities that are involved in the entire process of token issuance, sale, purchase, and investment. With the use of the proof-of-work POW mechanism in Bitcoin, it was demonstrated for the first time that computer protocols can be designed in such a way that attacking a system does not result in achieving an uneven advantage or commercial benefit. This concept then further matured into what we call today crypto economics, This can also be understood as a combination of economics, game theory, and cryptography. Token engineering. Token engineering is an emerging concept that is looking at tokenization from an engineering perspective and is striving to apply the same rigor, systems thinking, and mathematical foundations to tokenization and blockchain in general that a usual engineering discipline has. This subject is still in its infancy. However, good progress has been made toward the development of this new discipline. Token taxonomy. There is a lack of consistent taxonomy for tokens. As such, there are no clear standards defined on how to design and manage tokens. Also, it is not clear how to reuse an already existing and working token design, or if any exists at all. Therefore, there is a need for a classification system that categorizes all different types of tokens according to different attributes they have. There is also no universal classification of different attributes of tokens such as type, value, and economic attributes. Such a system would benefit the tokenization ecosystem tremendously. Some work on this was started by Interwork Alliance by producing a Token Taxonomy Framework, TTF. More details on this work can be found on their website, interwork.org. Summary. In this chapter we covered tokenization and relevant concepts and standards. We also covered different types of tokens and related token standards. Moreover, a primer on trading and finance was also provided to familiarize readers with some standard finance concepts, which help us to understand the DeFi ecosystem too, as most DeFi terminology is borrowed from traditional finance. Also, we introduced a practical example on how to create our own ERC20 compliant token using the Ethereum platform. Finally, we introduced some emerging ideas related to tokenization. In the next chapter, we will explore how blockchain can be used outside of the context of its original usage, that is, cryptocurrencies. We will cover various use cases and consider in particular detail the use of blockchain IoT.